You learned a lot about the JavaScript syntax, the core JavaScript features, and how to write amazing JavaScript-driven applications, both on the front end, so in the browser, as well as with Node.js on the server side. Now, one topic we haven't really touched on thus far, or haven't really talked too much about, is security. And of course, security matters. In this module, I want to highlight what you should watch out for when writing JavaScript code, and some common pitfalls or some important things you need to keep in mind to ensure that your code is secure and you're not exposing security relevant data or anything like that in your scripts and so on. Specifically, we'll have a look at potential security holes and things to watch out for when writing JavaScript code. I'll of course also let you know how you can protect your code or which steps you can take to ensure your code is protected. We'll have a look at some common attack patterns or security concepts like CORS, which I already talked about, but which I will repeat here, CSRF, and most importantly XSS, which stands for cross-site scripting attacks. And I'll also have a look at NPM packages or third-party libraries in general again, because these, as it turns out, can also lead to security issues. So now let's not waste any time, let's have a look at what you should be aware of and how you can secure your code. So what could go wrong when we write JavaScript code or when we expose our JavaScript code? For that, we also have to differ between writing code that runs in the browser and writing code that runs on the server. And I will start with something that is only relevant if you're writing browser-side JavaScript code. And that would be security details in your code or private information in your JavaScript code. We'll also have a look at cross-site scripting attacks, though, which is also relevant for browser-side JavaScript code. I'll briefly touch on cross-site request forgery or CSRF attacks, which is related to both front-end and back-end code, but which only works or only is a thing if you have some backend you're sending data to, and therefore I'll briefly talk about that as well. And I'll revisit this concept of cross-origin resource sharing we already talked about earlier. So let's start with the security details in your code. What do I mean with that? The important thing to understand about JavaScript in the browser is that your JavaScript code is part of what the browser downloads and runs, well, in the browser. So all your code runs on the machine of your page visitors. And it's important to understand that your JavaScript code can be read by them. Anyone who's visiting your page can read your JavaScript code that runs on this page. It's not hidden, it's not compiled to some unreadable machine code. It's totally available to anyone visiting your page, and that is super important. Therefore, any security relevant details you have in there, any confidential data you have in there, is exposed to your users, and therefore it should not be in there. You should not have security relevant information or confident data in your client side, in your browser side JavaScript code, because attackers may be able to abuse that exposed data. For example, if you have your database credentials in there, attackers could read them and could connect to your database to then read your data, change your data, or do whatever they want to do. Or if you're storing some client-related data, so about all your users, not just this user who's visiting your page, but all users of your page. If you have something like this in your browser-side JavaScript code, well, then anyone can read it and you might expose information about other people to all users. So therefore, because of this database example or any other data that might be confidential, you should ensure that such data does not end up in there. And let me show you what I mean. I'm back in our practice application we wrote, so this application. And you might remember that in the debugging section, we had a look at the sources tab, and there we actually could read the source code of this page. Here in the assets scripts folder, there it is. Now, of course, here we're seeing the code after Webpack worked on it. This is the code in development mode, and therefore if you scroll enough, at some point you will find your actual code, and it will be quite readable because it's not minified, because it's not optimized at all. So all of this actually will be quite accessible and quite readable if you scroll down far enough. And therefore, anything you have in there is exposed. For example, if I scroll all to the bottom, where our script code should actually be found, we see here it's hinting at location.js, and if we scroll to the right, we actually find our code in here. This all inline code, that's our code. It's of course a bit hard to read, but it is readable. And it's not just us who can read that. Anyone visiting our page can read that. Now, once you build for production, this will be optimized and it will be more unreadable, but there are tools to make it a bit more readable, actually built here in the DevTools. If you click on Pretty Print, this code is formatted such that it's a bit easier to read if it were minified. And besides that, if someone is really interested in getting your data, there are certain pieces of data, like your database connection string and your password, which is just a string, which of course will always be the same string, no matter if the other code is minified or not. So such data can be found and can be used. So any data which could be abused by other people should not go in there, should not go into your client-side JavaScript code. Now, in this project specifically, you might be wondering about things like our Google API key. Isn't that, for example, a security relevant detail? Well, it could be, but in Google's case, or in the Google API key case here, you can actually restrict the usage of that key in your Google Developer Console. There, you could restrict that only certain IP addresses can use that key, so that only the IP address where you are hosting your application can really send requests with that help of that key. And if anyone steals that key and tries to use it, Google will block requests by that person's IP address. So this is some security mechanism which a lot of APIs offer if you use their API keys, and therefore this is not a security relevant detail. That would be a different thing though, if we would expose data from our backend from this Node.js application. Now keep in mind here, I loaded a different project. This is the Node.js application we wrote, and there, for example, in the location.js file, we are connecting to the MongoDB database. Here I got my password and my username I used there. Now, this is data which is not exposed to our users because this is now actually only running on the server through Node.js. This runs on a machine and the user will never be able to see that code because this JavaScript code is never sent to the user. It's never attached to the outgoing HTML page. It's not loaded by any outgoing HTML page. So this code here is secure. It runs on a server, and unless users can access our server, which of course requires them to effectively hack our server, they can't read that code. So this code is secure. But if this code here were in our client-side JavaScript code, so in the code which is loaded by the browser and which the user can see, then users could see that data and abuse it. So long story short, don't put any important confident information into your client-side code. Users can read it, and there is absolutely no way for you to avoid that. You can make that code harder to read, you can minify it and so on, but it will always be readable and people can therefore read it. So don't put important information into your front-end code. Now let's move on to the next attack, which is the most dangerous attack, or the most dangerous attack pattern you can expose in your client-side JavaScript code. And I'm specifically talking about the client side, so about the side which runs in the browser, because the server side by default is way more secure. And when we talk about server-side attack patterns, they are not specific to JavaScript, whereas cross-site scripting and exposing security details is. So for the server side, there is a different range of potential attacks, one of them being CSRF attacks, others being SQL injection, for example, if you use a SQL database. And I'm not talking about them here because they're not primarily related to JavaScript. In my Node.js course, which talks way more about server-side code writing and so on, I do talk about more security holes you could expose on a server in general. So back to the JavaScript specific ones, and they are to cross-site scripting attacks, also shortened or abbreviated with XSS. This is an attack pattern where malicious JavaScript code gets injected into your application and is executed there. Now I'll show you an example for this because it can sound abstract at first, but this is really a dangerous attack pattern. You have to imagine if people are able to add code to your application, which all users of your application therefore execute, they are effectively executing code on the behalf of these users and at the same time on the behalf of your application on the machines of those users. And your code can do anything the code you write could do as well. So your code could send requests to certain domains, which might allow access by your application with the right CORS headers. The code might read the local browser storage of the user and send that to some server of the malicious user who injected the code, and much more. If you're able to inject JavaScript code into another page so that it runs for every visitor of that page, you're able to gather a lot of data about these visitors, potential security relevant data included, and you're also able to fake a lot of things and send a lot of requests maybe to your own malicious pages on the behalf of the application and on the behalf of the users visiting that application where you're injected your code into. So that's really dangerous. You got full behind the scenes control if you inject code into another page. An example for that would be unchecked user-generated content. And I want to show you that example so that you understand what the problem is. When we talk about cross-site scripting attacks, let's go back to our application here, to this share a place application. And there, let's generate an address, 6th Avenue, find that place. And then we have this shareable link here. This is the link which does not use our backend code with a database, but which encodes all information into that URL. This attack pattern would also work with a backend database though, and I will come back to that in a second. So here we have this link. We can visit this page and we see this page here. So that's of course not too fancy. How could this be insecure? Now if we have a look at our code, there we have the myplace.js file, and this is the file responsible for displaying the page and this title here on this page once we visit this link with the encoded information. Specifically there we set the title text content to our address. Now what if we would set not the text content here, which just sets the text node, but inner HTML, either as a mistake or because we actually do expect address to be more than just a plain string, which it is in this application, but which it might not be in all applications. And therefore, since this might be HTML code we want to output, we want to set inner HTML to not just render a text node, but all the HTML code, which is inside of address. And if I do that and I save that and reload, get the same output as before. However, if we inspect this in the developer tools, keep in mind we're setting the inner HTML code of the h1 tag, and what we set there is in the end what we send to address, which is currently this part of the URL. Now what if this part were actually a script, however? What if I prepared a URL, which I want to share with other users, which contains a script as the address? And not every user might carefully look at that URL, and therefore this might not be seen by all users who visit this page with whom I share this link. So there I could try to run an alert where I say hi there and hit enter. Now what you see is now this is injected here. Now we don't see a title here, instead we see the script was indeed added here because I'm rendering this as inner HTML. Now you also see it doesn't seem to execute though, because actually modern browsers have a security mechanism where they don't execute script tags which are output with the help of inner HTML. Because of this exact scenario that you try or that someone tries to abuse a security hole in your application and inject JavaScript code which executes on your behalf. Also keep in mind that normal visitors of the page, of course, would probably not see that. They might wonder why they don't see a title, but they don't typically check the developer tools to see what's in there. So they might not see that. Now still, this doesn't really seem to hurt us. It's certainly unexpected, but since the browser doesn't execute the script, we're fine, right? Well, turns out there's more than one way of executing script code. Besides these script tags, which indeed are prevented by the browser to execute, what if we added an image here with a source that does not exist, and then an onError handler, where we then instead execute our JavaScript code. This is a valid HTML element, Now the source is not found, therefore on error should trigger, and we can add this kind of event listener to our elements. We as a developer don't want to do that because it's not really a good way of writing code, but as an attacker, it's great. We can add JavaScript code that executes right on an HTML element. If I now hit enter, indeed, we should see hi there, in Chrome at least. And we see that here because this HTML code is injected here. This image tag is injected here. The source is not found, so the onError handler executes, and therefore this script, this alert, executes. Now this alert, of course, is just annoying, but keep in mind I can share this link with anyone. I can post it in a Facebook group for people to visit it. And of course, an alert is not that dangerous, it's just annoying and unexpected. But here we could be doing other stuff too. We could be doing anything which might be security relevant. I could write a script in here, and yes, we can write a longer script in here simply by separating our lines with semicolons, where I access the local storage, read data from it, or read data from the local cookies, and send that to my own malicious server, for example. Visitors of the page will not see anything there. They don't get an alert, they don't get an error. I could even, if I'm really bad, in addition, render a h2 tag here with 6th Avenue. And then people might not see anything. If I now hit enter here, you don't get an error. Okay, I didn't format this properly, I should fix that. But other than that, the page works as it should. And here in the onError handler, in this script, we can do whatever we want as an attacker. We can steal confidential data from browser storage. We can send requests on behalf of the user who visited this page with this link to any backend we want. And that is therefore really, really dangerous. Here, this is a security hole we have in this application. We have this hole because here we're outputting inner HTML. Now, how can we fix that? One solution to fix this XSS security hole we have here is to use text content instead of inner HTML. If we do that and we visit this, you see now the code which previously was executed and rendered as HTML is now output as text, and therefore if we had any JavaScript code in here, like for example our alert again, where I say hi, would not execute. So now we automatically are not vulnerable to cross-site scripting attack. And if you never use inner HTML anywhere in your code, you of course rule out a lot of potential attack patterns. But with that alone, you're not totally safe yet. For one, sometimes you might need inner HTML, so then you need a way around potential malicious code. And in addition, it's not just inner HTML. If you're, for some reason, setting the onError handler of some HTML element dynamically to some user-generated content in some way, maybe you just want to have a user-generated text, which is output in here, well, still then, whenever you inject any user-generated code anywhere into the DOM, this could be a potential issue. So you always want to make sure you either inject it as only text with text content, or if you set some other attribute of an element to some user-generated content, and potentially JavaScript code could execute there, like with these onError and so on handlers, then you want to sanitize the user-generated content before you output it. So for example here, if we really needed to use inner HTML, we want to sanitize the content before we output it here. Now sanitizing means that we strip away any JavaScript syntax we might have in there. That starts with simple script tags, but should also include common keywords like alert and so on. Now how can you work around the problem that you might need to inject user-generated content somewhere where JavaScript could execute, so you have no way of using a text content node here, for example, and you still want to make sure that the user-generated data you're getting here is secure and doesn't contain any scripts that execute? You can use packages like sanitize HTML. This is a package which basically helps you sanitize text and remove any unwanted tags in there, so that invalid code doesn't execute in there. Now, one important note can be found here in the description right away. This sanitization actually should be done on the server if possible. That simply means that if we were in our Node.js application here, we might want to store any user input we get, so in our case the address, before we put it into the database. So we sanitize it with this package, for example, on the server side before we store it, so that the sanitized code is stored in the database. Because that's all something I mentioned. This attack pattern does not only exist if you can inject it into the URL, it also exists, of course, if you store something in the database. Because here I could be entering my malicious code like this, click find place, and if find place triggers our server to store this on the database, in the database, then we have a problem. So I want to make sure that whatever I send here is validated on the server before it's stored in a database. And you can do this with sanitize HTML as well. You can also use this in the browser, but that is a bit too late. It's not too late from a security perspective, but you still might have hacked or adjusted code in your database, which you also don't want. It doesn't do any harm there, but it's not ideal. If you ever forget to sanitize in a browser, you then have an issue. So try to sanitize on the server, not on the browser. Anyways, if you wanted to sanitize then, well, then you would just need to make sure you have this package installed, and you then can run the sanitize HTML function, pass your user-generated content, so the variable which holds the content the user has, to sanitize HTML, and then it will strip away things like that. It will ensure that this is not part of the output, that instead you are able to render HTML, but only secure HTML. This is what sanitize HTML does. Now, how do you use that package? Well, you can actually use the Node.js recommendation here. Run this command here in your project. So I quit my dev server and run npm install sanitize HTML with the -- save flag. Now this will install it here as a dependency. And in myplace.js, we can now import sanitize HTML from sanitize HTML. And now here, whenever we want to output or inject some user-generated content into an inner HTML tag or into another place where JavaScript could execute, we run sanitize HTML address in this case here. And if I do that, and then we restart the development server here, with this added and the file saved, you will see that now if I reload this page here, the alert is not thrown. Instead, now I just have my header here, even though I still have my dangerous code in there. But that was stripped away by sanitize HTML. So just to show this again, if I remove that and we reload it, we get the alert. If we add it again and I save it, we don't get the alert. So now we protect ourselves against cross-site scripting attacks. Again, this is best done on the server before it's stored in a database. But in this example here, in this app where I don't have a server side, where it's all client-side code, where it's just data that's part of the URL, then of course, our only chance is to do that sanitization in the browser, and then we can do it like this, and we're now making sure that this specific cross-site scripting attack hole is fixed. So I talked a lot about cross-site scripting attacks, but this is an important and very dangerous attack pattern. There also is another way of launching cross-site scripting attacks, which is also important to be aware of and to keep in mind. Let's say you fixed all your holes in your code by either using text content or in places where you need to render HTML code by using sanitize HTML or something comparable. Now, you still might be vulnerable to cross-site scripting attacks. And do you have any idea where they might be coming from? How could someone still get JavaScript code into your page, which then executes when users load your page? Let's say you fixed all these holes where you output user-generated content, which is the number one hole. Well, how about third-party packages? In this project, I'm using the Google Maps JavaScript SDK, for example. I do have this import here. And what this does is it downloads a script written by a team at Google, which then also, of course, runs on the machines of my users. Any third-party JavaScript package you add to your project executes code when your app runs because you use the code of that package. In the case of Google Maps, we use it in the map.js file. There we use that new Google Maps map thing. Where do you think is this coming from? It's coming from the Google Maps JavaScript SDK. So it is based on the JavaScript code we import from Google's servers. So we trust Google that their code is secure, because if it weren't, since this runs on the machines of our users, this of course would also be able to execute malicious code there. So when adding third-party libraries, you want to make sure that it's from parties whom you trust. For example, Google is quite trustworthy, of course, but you also, of course, need to be sure, or very sure at least, that these companies or library authors protect themselves against being compromised. You might trust Google, but if someone gets access to this code on their servers, which sounds unlikely, but if this is done by a frustrated Google engineer, let's say, then this person can, of course, rewrite this code which you import such that it still works, but that in addition to working, it does something malicious. So third-party libraries, of course, also can be hacked, and if they are, the malicious code that's injected into the library runs in your app and on the machines of your users. So you need to be sure that the libraries you're using are secure, that they're trustworthy, and that they're also defending against being hacked. So you want to make sure you're working with third-party libraries which are actively maintained so that security holes in the libraries are fixed, but at the same time where contributions, which in the case of open source libraries, which most libraries are, can be made by anyone, that contributions are checked. Of course, you can check the source code of the third-party library as well. And if it's a relatively straightforward, simple library, it might be worth scanning over that code and looking for anything strange. Does it try to access browser storage? Does it try to send HTTP requests, even though it's a library that shouldn't do that? Have a look at that and analyze that code. It might sound dumb, but this is a potential security issue, so you want to make sure you protect yourself against it. If you install something through npm, you also get a little hint. If I run npm install here to install all the third-party packages we're executing here, you'll see that once this is done, we get a little output here. Audited all these packages and found 0 vulnerabilities. Not every vulnerability it finds here is an issue though, and for some projects it will find quite a lot of vulnerabilities. It just means that there are potential security holes, which might also not be related to the code which is output to your users, but all these build tools which run on your machine and only on your machine as a developer, and therefore might not be as dangerous. But still, it just shows you that if there are vulnerabilities, you might want to check the versions of packages you're using and consider updating. Now again, you shouldn't freak out just because you find some vulnerabilities here, because most packages you use in modern projects only run on your machine. And of course, this is also not what you want, that you have a potential security hole there, but at least you're not sharing this code with all users of your web page. So therefore, this might not matter as much. And a lot of vulnerabilities are really just that, a vulnerability, not necessarily one which is getting abused at this point of time. Still, having a green 0 here is nice to have, but even more important is that any packages you use that end up in your code, like the Google Maps package here, that these packages are also trustworthy and secure. You never have 100% security, but you should of course aim for as much security as possible. So that were cross-site scripting attacks, the most dangerous attack pattern when we talk about JavaScript code. They only affect browser-side JavaScript code, but since this is the part where you typically run a lot of JavaScript code, it is a thing you definitely have to watch out for and you have to be aware of. Now with that, however, let's move on to cross-site request forgery. What is this attack? It can be related to cross-site scripting attacks, but it doesn't have to be. The idea behind cross-site request forgery is that people trick you into clicking on a link that leads to a prepared page where they abuse your local cookies to then send a request to the page you would normally talk to as well, let's say your online banking backend. But since you're coming from a prepared page, you then do something there automatically without you recognizing that you don't want to do. For example, send money to someone you don't want to send. Maybe that even is possible to happen behind the scenes without you noticing. So this attack pattern also depends on injected content, so injected JavaScript code, but it can also be just HTML content which submits a form to the trusted server. The problem is that the form is part of an untrusted page, which you might not recognize if the URL looks similar. And then requests on your behalf with your cookies can be made to the trustworthy server. So the only danger and the only problem is that this is all happening from a malicious site. So actions might be executed on that trustworthy page with your data without you knowing that it happens, and therefore you might want to protect against that. Let's have a closer look at this pattern, though I do talk about it in more detail and also how to prevent it in my Node.js course, because this is more a server-side issue. You need to protect against CSRF attacks on the server side by using a mechanism which is a CSRF token. And again, I do discuss this in my Node.js course where we work on the server side on the backend all the time. So CSRF stands for cross-site request forgery, and the idea is that if you're the user of a web app and you have some backend, let's say the online banking site which uses Node.js or any other programming language, this is not exclusive to JavaScript, uses any programming language and it talks to database, the server. Now you're visiting the front end of this page, let's say the user interface of your online banking site. And now when you have such a setup, typically the server-side application identifies you with a so-called session. So you logged in and then the server-side generates this session object, stores session data on the server and sends you the session ID which is stored in a cookie. That's a typical authentication setup you have in web pages where front-end and back-end work together. Now then you might be sending an intended request, for example to send money to B, and all is good. The problem is that if you now visit a fake site because someone sends you a link to it, which looks like the trustworthy site but which isn't, then you visit this page and there people send a request to the trustworthy backend. Therefore, the browser attaches cookies that belong to this trustworthy backend, which is your session ID, for example, and everything works. The problem just is, since you're on a fake site, the request might one that is intended by the fake site but not by you, for example to send money to C. And this request will succeed because you sent the right cookie, the right session ID, and you send it to the right backend. So again, more details can be found in the Node.js course, but this is also a potential attack pattern, but not directly linked to JavaScript. It can be implemented with cross-site scripting attacks, but it can also be implemented by using such a fake site, which does not require cross-site scripting attacks. So therefore, this is not really a JavaScript security thing. It's more a server-side or general web application security thing, and therefore I do discuss it in more detail in my Node.js course, where we write a lot of server-side code. The last security hole you should be aware of, or the last security relevant concept you should be aware of to be precise, is cross-origin resource sharing. And I did talk about this earlier already. It's not really an attack pattern, but a security concept. The idea here is that requests from your browser-side application can only be made to a backend, so to a server side that runs on the same server, so that the HTML page and the script that executes there was served by the same server you're trying to send a request to. That's how browsers by default work with your pages. This is what they allow by default. Now, in modern web applications, you often need to send requests to other servers though. So a server which did not serve the running HTML and JavaScript code, but which only provides some API endpoints, some URLs to which you can send data, to store data, or to fetch data. This is something we had a look at in the Node.js module. Then you can control via server-side headers, and only via server-side response headers, whether this request, this incoming request, is allowed and you send back a valid response or not. So this is a concept where by default browsers would not allow you to reach out to some other server, but with the right server-side headers you can override this. So it's a concept which in the end should secure servers so that not everyone can access their resources, not every page can access their resources at least, but with the right headers on the server side, you can allow this. And an example for that actually would be JavaScript modules. This built-in JavaScript concept also required a development server, if you remember. And it required a development server because JavaScript modules, so JavaScript files you import into another file, are only allowed if they're from the same server. So I'm only used to import another JavaScript file which sits on the same server, which is served by the same server. And here we have no real way of changing this because that's a built-in security mechanism by browsers specifically for this JavaScript feature. Another example though would be the Node.js application we worked on. There we have our different routes which we handle on the backend, like add location, and the request which is sent there is not sent from some page that is served by the same server, it's sent by a page that runs on a different domain on a different server. And still it works because here I set these right course headers, which tell the browser that's okay, this page which sends the request is allowed to get the data, and therefore the browser won't block it. So it's a security mechanism which you can use or disable or configure to your needs based on your requirements. That's the idea behind CORS, this cross-origin resource sharing concept. This is it for this module. The two most important attack patterns or vulnerabilities I want you to take away from it are these two: security details in your code which you expose accidentally, and cross-site scripting attacks. These are the JavaScript specific attack patterns, whereas the CSRF pattern works with any language on the backend and with no JavaScript code in the frontend, and CORS is a general security concept. But the two leftmost holes, security holes, are the important ones you might have in your application. If you expose code there, all your JavaScript code is always readable by anyone. That's something you have to keep in mind. Exposing important information in your JavaScript code allows anyone to read and abuse it. And cross-site scripting attacks allows users to prepare data or prepare links which all visitors of your page might then see, and if that data, this prepared data, contains scripts that executes, then for all visitors of your page, these scripts will execute and can do dangerous stuff, like read personal data, send malicious requests with user data to some malicious servers, and so on. So you definitely need to protect against these two security holes, for example, by sanitizing output, by using text content instead of inner HTML, and by not leaving any important data in your JavaScript code. We worked on our application, we tested it thoroughly, we're happy with the web page we created and with the JavaScript code that runs on it. No matter if we just wrote some client-side JavaScript or if we built a whole server-side application with Node.js. Now the goal is to deploy that application. You want to make sure it does not just run locally on your machine where you test it, but you want to put it on some server, on some computer in the web, which has its own domain connected to it, its own IP address, which is reachable by anyone, which your local machine thankfully isn't, so that all users that are interested can start using your web application. This is ultimately the goal once you're done with development, right? And this is exactly what we'll have a look at in this module. We'll have a look at deploying both a web page which only consists of HTML, JavaScript, and CSS, so which has no server-side code attached, and we'll also have a look at how you would deploy a Node.js application where you of course have JavaScript code that needs to run on a server. So let's dive into some theory first. It's important to understand that there are two main kinds of web applications, websites you could be building. One is a website that only consists of a bunch of HTML files, some JavaScript, and some CSS. This is what we actually worked on for the majority of the course. We didn't have any server-side code there, any code that needs to be executed outside of the browser of the user. But in the Node.js module, we did have a look at that because Node.js is a JavaScript runtime, which allows us to run JavaScript anywhere, including on a server, so on a computer, which runs somewhere in the web, which users can send requests to, but where they don't see the code. So not code that runs in the browser and therefore on the machines of our end users, but code that runs on a server we rent, we pay, and we put our code on. Now, for server-side code, Node.js is not our only solution or our only alternative. We could write this code with PHP and so on, but since this course is about JavaScript and Node.js is a runtime for JavaScript, I of course picked Node.js here. So these are the two kinds of applications we have. One which only has client-side code, and one which might also have client-side code, but which also has code that needs to run on a server, like in this Node.js example. Now, in the client-side code, in the left case here, all we need to serve this website to our users is a so-called static host. This is a host, this is a web server, a computer configured such that for incoming HTTP requests, it returns the HTML files and the JavaScript and the CSS files and maybe any images you're using, but that it does not run any JavaScript code or any server-side code on itself. So put in other words, it's a machine, it's a computer somewhere in the internet with its own IP address attached to it and connected to a domain maybe, which simply does not have Node.js installed on it. Instead, you just put your files onto that server, configure it briefly to return these files for the incoming requests, and you're done. Now, you could configure such a computer all on your own, but typically you would use certain services for that, which makes this configuration and so on way easier and more secure, and you simply pay for these services then. And I will show you examples for both deployment scenarios, static and non-static, in this module. Speaking about non-static, you could also call this dynamic. You need a dynamic host. You need a computer somewhere in the internet connected to the internet, in both directions, so that it also is able to handle incoming requests, which has, in our case here, Node.js installed on it, so that on this computer you can execute JavaScript code, which is not possible in the left scenario. But in the right scenario, the server-side code scenario, we have a web server which does not just return HTML, CSS, and JavaScript files to the users, so that the files are then handled locally on these users' machines, but which in addition to that also is capable of running, in our case, JavaScript code on the server itself by simply installing Node.js there in the end and by, of course, configuring it correctly. Now, just like in the static scenario, you could theoretically set up such a machine all from scratch on your own, but you need advanced server administration knowledge for that to do that in a secure and scalable way. Therefore, in both scenarios, you would typically use certain services for that, paid services which do the heavy lifting for you and allow you to simply put your files there, write some basic configuration, and be done for it. So these are the two options: a server that just needs to host and provide these static assets. Their example hosting services would be S3 by AWS, so by Amazon Web Services, Firebase hosting, and many more. If you Google for static web host and so on, you will find plenty of results. In the right scenario, we need a server which is able to execute our files or our scripts on the server, our server-side scripts at least, and their example services would be AWS Elastic Beanstalk, which is a service by Amazon Web Services, Heroku, and again, other services as well. Now, this is the overview. We'll have a look at both approaches in this module. Before we move on to the concrete deployment with the example services I picked for this module, I first of all want to walk through the general deployment steps though. So what's the deployment process? Of course, it all starts with us developing, with us writing our code. That's what we did so far throughout the course. We also want to test our code. We want to make sure it's error-free, it's secure, it has no bugs. That's also what we did throughout this course. We continuously went back into the browser and tested our code there. So this is also an iterative process here. We write code, we test it, we go back, fix bugs, and so on. Now, once we're done with all of that, we can do some optimizations. We can write fallbacks to offer a good browser support. We want to look up the browser support we need. We also use build tools like Babel together with the Webpack to optimize and shrink our code and add potential polyfills which we need. Then we can build for production production. Typically also with the help of Webpack, which then shrinks our code even more, which shortens the function names in the code it outputs, so that we ship and deploy as small of a code package as possible. For the code that runs in the browsers of our users, that's important, so that the application there is able to start up as quick as possible, so that the code there is loaded as quick as possible, and we're not causing any unnecessary delays and therefore a bad user experience. Now, this is also an iterative process, you could say, because you might want to optimize your code, optimize performance, something we'll have a look at in the performance optimization module. And then you want to test it again in production, so build your code for production, test it locally on a server, and so on. And once you're fully happy with the result, you deploy the output. So the built and optimized code, you now take that and put it onto a server. Now important, this here all applies to the scenario where we have client-side JavaScript code, so code that runs in the browser. For our server-side, our Node.js code, you could actually say that the optimization and build for production part is not that important, because since you ship it on your server and users never will download this code, it doesn't need to be as small as possible. It can be bigger, it doesn't have to be optimized, because it's just running on your server, which is super fast typically, and you save the time where the code would need to be downloaded. So this all applies to the code which runs on the client. Not all of that, specifically not the optimization and build for production part, applies to server-side code, at least not to the same extent. So now with that, let's have a look at that process in practice by having a look at both deployment scenarios, deploying a static app, so this left case, and deploying an app with server-side code, this right scenario here. So let's dive into this deployment process, starting with a web application, a website, which has no server-side code, which is only powered by HTML, JavaScript, and CSS, and which therefore needs a static host. Now, we clearly wrote our code. We tested it throughout this course, and if you're working on your own application, you of course also at some point tested it. Now we need to optimize it and build it for production, then we can deploy the output. Here's this practice app we worked on, and we wrote the code, we tested that. Now regarding the optimization and producing the deployment output and so on, for that we got Webpack. We got our Webpack configuration, both a production configuration and a development configuration, for testing this, for bundling this, and for production, for also optimizing this, which Webpack will do automatically if the mode is production. So here in package.json, we got this build prod script, and now we can simply run this. We can run npm run build :prod, and what this will give us is an output which we can ship to a web server to then host it there, to a static web server to be precise. So here we got our dist folder, and in the end, we just need to take that entire dist folder content and deploy that. Now, the only adjustment we specifically need to do here is our output. Our JavaScript files, of course, have this random hash in there, and we should respect this in our imports. So on these JavaScript files, in the end, you can copy that file name and take the myplace file and replace this import here in assets index.html with this name here, and do the same for shareplace. Now, you can also set up more elaborate build workflows where the HTML file is automatically adjusted, but this requires advanced Webpack knowledge and so on, and therefore we'll take this manual approach here. Now, once you did that, once you prepared these script imports in the two HTML files and you have your optimized script outputs here, you're ready to go and you're ready to upload it to a web server. We can ignore this warning here, by the way. It basically warns us that our myplace output is pretty big. Well, that's the case because I'm importing the sanitize HTML library there, which is rather big. Another reason for why you should do this on the server side and not on the client side, by the way. But we have it here for a good reason, because in this app we have no server-side code. So we have to live with that. Now, once we adjusted everything, we built everything, we're ready to ship this onto a static host. Now, as I mentioned, you could set up your own computer, connect it to the internet, allow incoming requests as well, and configure everything on your own. Well, This, however, is not easy to do. It's easy to do in a wrong, in an insecure way, so that your server could easily get compromised, and even in that way, it still requires some network knowledge to set up such a computer and connect it to the internet. Therefore, what you would typically do is, you would go for paid hosting. You can search for static web hosting, for example, and you'll find a couple of services, both in the advertisements as well as in the real search results, which help you host a static website. For example, AWS, the Amazon Web Services, have a service that makes that easy, the S3 service. There are other services as well, and one service I like because it's really easy to get started with is Firebase hosting. Firebase is a Google service which offers more than just the hosting, but here we just need the hosting, so we can use that. You can click on that Firebase hosting search result here, and it takes you to the Firebase documentation where you can learn more about Firebase, Firebase hosting, and how to use it. And of course, here you can also learn more about the other Firebase services in case you should be interested. Now, one important word about pricing. Firebase is free to get started with, but it does have paid parts or paid services or certain usage limits after which it is no longer free. And you can check the Firebase pricing pages to learn more about the pricing. You can get started for free without a credit card though, and it will basically tell you when you need to upgrade. But be aware that not everything is free there. Of course, you will have to pay for the more advanced services or more heavy usage, but getting started is free. Now here, what we can do is we can simply click on Get Started here, and we'll learn how we can get started with Firebase hosting. And it all starts with installing the Firebase CLI, for which you can click on this link here to be taken to a page where the installation is explained, and you can simply download an installer here. An alternative to downloading an installer here is that you simply use npm for the installation, and you run this command here on your machine anywhere. So here I'll run it in this built-in terminal, but that really doesn't matter. On Linux and Mac, you might need to add sudo in front of this command to get the right permissions. On Windows, this is not required. So after you hit enter, you might be prompted for a password, and thereafter this Firebase package will be installed globally on your system, and we'll need that package to then deploy our application. So let's wait for this to finish. And once this is finished, we can run Firebase init here in our project folder. So make sure you navigate into your project folder, or you use the built-in terminal in Visual Studio Code, which is automatically navigated into the project folder. Once you run init here, you might be prompted to log in first. So simply go back to Firebase and create an account there. You don't need to pay anything, it's free. Just create an account or log in with your Google account. And once you do have an account, log in here in the console by entering your email address and thereafter your password when you're being prompted for it. Once you did log in, you should see this menu here where you can choose from a variety of Firebase services, and we need the hosting service. So navigate there and press space to select it, and thereafter press enter. Now you can choose your option here, and here I want to create a new project. This talks about Firebase projects which are created on Firebase servers, and we don't have one yet. And you can enter any name here. I'll name it JS Static Hosting. You can choose any name you want here. Now this actually was the project ID. Now you can choose a project name, which can be the same though. So I'll go with the default and just hit enter and not provide a different name. And now this will set up this Google Cloud Platform, which behind the scenes powers Firebase project, and make sure that this is all configured on Firebase servers. So let's wait for that to finish. And once this finished, you're prompted to tell Firebase what your public directory is, which in the end means which is the directory where your deployable files sit in. And in my case, that's not the default, a folder named public, but instead it's this dist folder. So we should write dist here to make it clear that the dist folder is the folder we want to deploy. Now once you hit enter, you're asked if you want to configure this as a single page app, which means that anything the user enters in the URL is redirected to the root index.html file. And here I don't want to do that, so I'll enter no here, N, because we have different folders with different HTML files. I don't want to redirect all requests to this top level index.html file. So enter N here and hit enter. You also get a 404 HTML file now, which is a default error page, which you of course can customize in case the user enters an invalid URL. And when you're asked if you want to override dist index.html, you should choose no, of course, because we want to keep the existing index.html file in there. And with that, we're done. Now you can run Firebase deploy here, and it will go ahead and deploy this project, which was just configured, to Firebase servers, which means it uploads your files in the dist folder to Firebase servers and configures everything you need there. Once this is done, it gives you the URL where you can find your application. So now here, if we enter a new tab, we can visit our application here. Also check the console. The only error I'm getting there is the fav icon, which is not found. That's okay. And now here, if I try to get my current location, I can allow this and check whether that works, whether I am being located here. Yep, that works. I can click Share Place and enter my shared place URL here to see this page. So this all works. This is our deployed project, our deployed static project, I should say, which only consists of HTML, JavaScript, and CSS files, which we now deploy to Firebase. And of course, the exact deployment steps, for example, the command line tool, which we used here, will differ from host to host. The general idea regarding the fact that you deploy everything in this dist folder and so on will always be the same though. So that's something which does not change. Also worth noting, in Firebase case, you get a Firebase RC and a Firebase.json file, which allows you to configure the exact hosting setup. And you learn more about the available options there, of course, in the official documentation, in case you're interested. So check this documentation out if you plan on using Firebase. If you plan on using a different service, which of course is fine too, there are many great services, check out this services documentation to learn about the exact steps you need to execute to get your code onto this services servers. So we deployed our static page with HTML, JavaScript, and CSS. What about our Node.js application now? Here we have code that needs to execute on the server, not on the client. Therefore, this is not a static application, it's a dynamic application because we have code that needs to execute directly on the server. And by the way, it does not matter if you have an application which produces HTML files and returns those, as we set it up at the beginning of the Node.js module, or if you have an application which just has a couple of routes and exchanges JSON data. That does not matter. You need to execute Node.js code on the server. That is what matters. So now we need a host that supports this, and Firebase is not such a host. Well, they do have some cloud function service which actually allows you to execute code on the server, but it's a little bit different. It's not really meant for this kind of deployment, even though technically there are ways of making it work. However, it's not what we will use here. Instead, if you, for example, Google for Node.js hosting, then you will find a couple of advertisements and of course all the real results that guide you towards Node.js hosting services. And of course you can perform a similar research for other languages like PHP as well. Now, one popular service for hosting Node.js applications is actually Heroku. It's of course again not the only one. AWS also has services, for example, but Heroku allows you to get started for free without a credit card, just like Firebase, and that of course is very convenient. Now, just as Firebase, it also does have paid services, and you should check the pricing pages there to learn more about that. But what I'm about to show you and these basic hosting demos, they all can be implemented for free there. So we can simply visit the Heroku page there, and it all starts with signing up, which you should do to create a new Heroku account, which you will need to then get started hosting your application there. As I mentioned, you can get started for free. You should check the pricing page to learn what costs you money though, and up to which point it is free and which limitations you have in a free account. So here I did log in now, and if you signed up, you should see the same screen in the end, and we can click on Create New App here. And again, every hosting service of course differs regarding the exact steps you need to perform, but the documentation of the hosting service you chose will be the place to go to learn how to get your application to run on that service then. Here I'll again name this JS Node.js deployment, any name you want. Choose a region where it will be deployed. I'll go for United States. Create app, you don't need to do anything with that pipeline. Now you've got a couple of options here regarding how you want to deploy. You should go for a Heroku Git here, for which you need to have Git installed. If you Google for Git, you'll find that git.scm.com page. Git is a version control tool which allows you to create multiple snapshots of your code whilst you are developing. It also can help you push your code to remote repositories where you can store it, or in the case of Heroku, to Heroku's servers. And you can simply download Git from this Git page. Simply choose download here. It should automatically select your operating system. Otherwise, you can select it from down there. And walk through the installer that gives you. This will install Git on your system. Attached, you also find a link where you can learn more about Git and get started with it, though here we won't need to do too much with it. Instead, let's go back to Heroku's page here and make sure you also download the Heroku CLI, or you install the Heroku CLI. Now for that, if you scroll down to download and install, there are various ways of installing it, and you can follow the instructions given here using the Windows installer, or using this command here on Mac, for example, or using the Mac installer if you can't use that command here, and so on. You can also use other installation methods here, as you see. So in the end, you should be able to get this Heroku CLI onto your system. Now once you got the Heroku CLI installed, you can run Heroku login. So here I'll copy that in my project folder. And now you need to enter or confirm, if you already were logged in, your email, and then enter your password. Now once you are logged in, you can continue with these steps here. If you installed Git, which you need to have installed, you now have a Git command available which you can run. So make sure you navigate into your project folder, which you already are here with the built-in terminal, and run git init unless you already are managing this folder with Git, which I am doing here, and you might or might not be doing that already. So otherwise, if you're never used Git before, simply run git init in your project folder now. Thereafter, you can copy this command here and simply paste it in here in your project terminal and hit enter. This will now basically configure your project here to be deployed as a Node.js application to this Heroku application you just created. So once you did that, these are the 3 commands which you now need to execute to get your code onto your Heroku app in the web here, so to basically deploy your files. Now I already added files and created a so-called commit, which is basically a snapshot in code. So I will just move on right away to this git push Heroku master command and execute this. And what this does is it now takes my latest snapshot, which you created with the add command and the commit command, and try to push that to Heroku's servers. Now here it actually failed with an error message that no default language could be detected for this app. So with that, a programming language is meant. To fix this, go to your package.json file and add a new script there. You name it start, and then simply write node app.js here. This in the end will tell the server how it then starts your server. So with this script added now, let's create a new snapshot with git add dot and git commit -m added entry script. And thereafter repeat that git push Heroku master command, which failed before. If it still fails, like it does for me here, create a new file in your project, a proc file, simply name it like this, no file extension, and add this line into it, web : blank node blank app.js. So this is then your start command here. And a proc file is a file Heroku specifically looks for. So then let's again run git add, git commit, added proc file, and thereafter repeat that push command, and at this point it should certainly succeed. If it succeeded earlier, that's of course also fine. Now with that, you can go back to Heroku and there click on open app, and this now is our server for this application. Now of course the application we deployed here is a Node application which doesn't return any HTML code anymore. Instead, this connects to a database and gets data from there and allows us to add data there. So for example, we can send a request to this URL here and replace our location ID here with some ID we might have or with some random text. And if we now open the console or go to the network tab to be precise and reload this, we'll of course see that this request fails. Now obviously it fails because this server will actually not successfully connect to our cloud database here, to our MongoDB database, because there we haven't whitelisted the Heroku server yet. So here you would have to go to network access and actually make sure that all IP addresses, so access from anywhere, is allowed. People still need your username and your password, but now we're not restricting this to our local IP address anymore. And since Heroku, in the free setting at least, always assigns a new IP address, we want to allow all IP addresses to be flexible there, because we won't have a fixed IP address. So we'll have to do that to make sure that Heroku is actually able to connect our Node.js application, or with our application, to this database. So let's wait for this to update here. And with that completed, go back to your Heroku management page here, and under More, restart all dynos, which basically means restart your server, which we want to do here to make sure that it cleanly restarts again, because it will have crashed before. You can go back to your web console and click on Open App. Now this will open your deployed application here in the browser. Now of course for this default route it will not find anything, because in the application we deployed we only have 2 supported routes set up in the location.js file. And by the way, it does of course not matter whether you have a page that returns HTML or you have a page that exchanges JSON like ours. You need to visit a route that exists, unless you have a general fallback route, which we here haven't. We have no 404 fallback route. So now we can, for example, enter this URL though. Of course, enter something here instead of that dummy placeholder for the ID, and hit enter. Now, chances are that this will take very long and or crash at some point. The reason for that simply is that this is an invalid string to be used as an ID. And therefore here, when we try to convert this to an object ID, this will actually fail, cause an error. And since we have no proper error handling here, which you of course would learn about in my Node.js course, this crashes. Now again, I do cover error handling in great detail in my Node.js course, of course. Since that's not the focus of this course, I decided not to dive deeply into it. Here the problem is that we have an unhandled error, and therefore our server crashes after some time. Theoretically though, it would work. And just to prove this, I searched for the ID which we used in the past, which we created in an earlier module. I'll restart my server here, because it crashed. And of course, therefore, you should have error handling in a real application. But here I'll restart it, and I'll try to fetch data for my valid location ID here. So this alone won't do the trick though. It will still fail, and the reason for that is quite trivial. One preparation was missing. In app.js, I'm listening to port 3000. Now actually, when we plan on deploying this to a real server, we don't want to use this dummy port, which we only use locally. Instead, we want to use the port the server we push this to assigns to us. And we can tell Node.js to do that. We need to define the 3000 as an alternative here by adding 2 pipe symbols in front of it, and instead refer to process.nth.port here as a main value. Now what does this do? This looks strange at first, but this uses a system built into Node.js called environment variables. This in the end is a placeholder where the concrete value will be injected dynamically by the environment that runs our script. Now if it's not provided, for example during development, when we start the script, we'll fall back to 3000. If it is provided, however, and Heroku will provide a value for this port variable, this provided data will be used instead. So Heroku can provide its own port where we want to listen, instead of that 3000 port, which is just there for development. So now with that, we just have to add this change here. Added port nth. And then again push this to Heroku, and there wait for the installation and the build process and the startup to finish. And thereafter we should be able to visit and run our application. So let's wait for that to finish up. And thereafter, once you revisit this page, you should get your location data. So this is how you could deploy a Node.js application to Heroku. Of course, Heroku is just one of many hosts. A couple of steps are always the same though, like providing this environment variable. Catching errors is a good idea, which you might consider implementing. You also want to make sure that you whitelist the IP address of the server where your application runs, or if you don't know the IP or if it changes frequently, you whitelist all IPs as we did it here. And with that, you're able to also deploy applications that use JavaScript on the server, namely Node.js. So you learned a lot about the JavaScript syntax and how to write JavaScript code, and obviously that's what this course is about. Now, in this module, we'll also dive in an important related topic, and that would be performance optimizations. Because of course it's nice that we're able to write JavaScript code, but we want to write good JavaScript code. And most importantly, you should be able to find out whether you wrote code that offers a good performance to your end users, or whether there are things you can improve or you might need to fix to avoid a bad user experience. Specifically in this module, we'll have a look at what exactly performance is, because it turns out that is rather a broad term and it can be a lot of different things. We'll also have a look at some tools or approaches of measuring and analyzing performance and of finding out how our application behaves. We'll also dive into some potential optimization ideas on how you could improve your code and what you should watch out for. And I will also guide you to some additional resources, because the whole topic of optimizing performance does not stop at JavaScript, what this course of course is about, but actually includes a broad variety of things. And even for JavaScript, it turns out there are a lot of different use cases. So in this module, I want to get you started. We'll dive deeply into all the important concepts, but thereafter I'll also give you the tools so that you can build up on this and analyze and optimize any part of your website, of your web application. So let's dive right in. So what is performance? Now, when we think about performance in the context of a website we're visiting, performance can be a lot of different things. But I think there are two main categories into which we can split this term performance. We can have a look at the startup time of a website, of a web application, and we can have a look at the runtime performance. Because these are really two different things that, of course, in the end work together and which both matter. Startup time is all about the question, how long does it take to see something on the screen, and how quickly is a user able to interact with the page. We all know how it feels like when we visit a page which is slow, which takes forever to load, or which at some point seems like it loaded, but when we try to click something, nothing happens. So we all know that. And therefore, this is, of course, one important part. But then once a page did load, of course, it should also offer a great performance and also avoid certain bugs. Here the question is how smooth the application runs in general. Does it occasionally freeze or lag? We of course don't like visiting pages where we, for example, try to enter some text into a text box and it takes us forever to do so because our input is only picked up with a lag. Especially websites or web applications, and I use these terms interchangeably as you can tell, with a lot of animations could end up in a state where we have a lot of visual lag, a lot of visual chank, where the animations don't play smoothly or anything like that, or where a running animation prevents us from doing anything else. Or, of course, we could have a website with certain memory leaks which add up over time. So, where some part of the code is buggy and actually occupies more and more memory the more often it runs. And depending on the device you're running this website on, eventually the device or the page might run out of memory and the browser might shut it down, therefore. So, that, of course, also something we want to avoid. But it's also important to understand that performance is not just about JavaScript, but about everything that's involved when it comes to, well, visiting and using a web page. It's influenced by a lot of factors. The CSS code and HTML code also play a role. If you have very complex CSS selectors, that takes the browser longer to apply styling. If you have a lot of unnecessary HTML code, that is more code which needs to be downloaded initially, hence slowing down the startup time. But of course, JavaScript is a major factor because that influences a lot of the parts related to runtime performance. And if you're downloading a lot of JavaScript code, it of course also influences the startup time negatively. Also, of course, The speed of the server you're hosting your website on, as well as the configuration of the server, can have a negative impact on your users. If you have a server that resides in the US and you have a lot of users from, let's say, India, well, it simply takes them a bit longer to get your data from the server. Now, of course, we're talking about milliseconds here, and it might not really have an impact, but the bigger your application is, the more users you're reaching, the more you want to think about all the factors that influence performance or that could potentially influence performance and optimize them. In this module, however, I will focus on the JavaScript performance part, but I want to put that out there that there are other factors which also play a role. Now, when we talk about JavaScript performance, what influences our performance there? When we think about our JavaScript execution, of course, here again, we have two different areas. We have the startup time. The question here is how fast the script loads and is able to execute. And we have the runtime performance. And here it's all about the work the script has to do and how efficiently it does that work. And it's not just about the work the script does on its own, but also about the interactions with our other web page. When you work with the DOM, for example, when you add and remove HTML elements via JavaScript, that can have a negative impact on the overall web application performance if you're doing this in a poor way, and I'll come back to that in this module. And of course, we have this memory thing. You want to avoid memory leaks to make sure that you're not slowing down the application over time, or that you even have the worst case scenario of the browser shutting down your application. Now, also it's important to understand that I talked about the browser here. I talked about the DOM. But of course, JavaScript, as you learned, does not just run in the browser. Now, the startup time, that's really a thing that is primarily related to the browser side. Because when we're talking about server-side JavaScript with Node.js, then there is no download delay or anything like that. The code already is on the server where it will get executed, so that whole startup time thing is less of an issue on the server side because all the code is already there, so therefore it can be executed very efficiently and quickly by default. But when we talk about runtime performance, that affects all JavaScript environments, all places where we can execute JavaScript. Of course, there are certain problems which can only occur in the browser. For example, when we talk about DOM interaction, but there also are other parts, other things about JavaScript which apply to both browser-side and server-side JavaScript. In this module, I will focus on the browser side because there we actually have more pitfalls, but we'll also have a look at certain things which you will see really affect any JavaScript code no matter where it runs. So we have these different layers of performance optimization, we could say. We have the startup time and the runtime. And now let's have a look at the different things which affect performance there. Now, of course, there are a lot of tiny factors which influence it, but there are a couple of bigger categories and potential improvements I'd like to think about when we have a look at these different layers. For the startup time, an important factor is the size of our script. So simply the question, how big is our JavaScript file we're forcing the user to download before anything is able to happen on the page? Remember when I said a couple of minutes ago that we have two parts when we think about startup time? The time it takes to display something on the screen and the time it takes until the user is able to do something with that screen? Well, the script size can affect both. If your script renders a lot of visual parts on the screen, then of course it affects how quickly the user is able to see something on the screen. But it most certainly will impact how quickly the user is able to interact. Because if your script is needed to add event listeners to a button and so on, then of course, even if the button is visible, the user will not be able to do anything with it if your script hasn't finished downloading yet and isn't available yet. So therefore, the script size, the size of the script file really plays an important role here. The bigger it is, the longer it takes users to download them, and the longer it will take users to work with your page. And keep in mind that not every user is visiting your page from a great internet connection. users might be using slow devices in slow network areas, and therefore even a script file which is only 100 kilobytes big can take a couple of seconds to download, and that could lead to a bad user experience. Now, besides the script size, it's also the amount of HTTP round trips. And I covered this earlier when we talked about JavaScript modules and when we introduced Webpack to bundle them into a single or a few bundles. And the reason for that is that if we're working with a lot of script files, and of course the same is true for a lot of CSS files, by the way, then the browser has to download all these files to make your page work. And every HTTP request that needs to be sent to download something has a certain base cost it takes to set up that request and send it, no matter how big the file is which you're downloading. So the more HTTP round trips it takes to finally have the final state of your page, the longer it will take until your page is ready to run. And therefore, this is definitely a part you want to optimize. And of course, we already started optimizing both the size and the number of HTTP round trips by adding Webpack, which does minify and optimize our code and which also bundles our code together. So now what about the runtime performance? There, it's of course all about optimizing our code execution. If we're working in the browser environment, that also includes one important aspect, and that is DOM access. So when we work with the DOM, when we add elements, when we remove elements. We want to avoid unnecessary code execution. We want to write code which is efficient to execute. And we definitely want to avoid unnecessary DOM operations. Because if we unnecessarily, for example, re-render too many elements on the screen, even though maybe just one element needs to change, then we affect performance. Because it turns out working with the DOM is really expensive from a performance perspective. Because JavaScript has to talk to the browser has to go through the DOM and find the place you want to change. It then has to create a new element. It has to add the element or remove one, whatever you're doing. And that all are a lot of steps. Now, of course, we're still talking about milliseconds here, but they can really add up. So being efficient here is super important, as you will see in this module. The other big factor are memory leaks. It's easy to introduce leaks, and not all leaks are horrible. You might not even recognize them. And I can tell you a lot of web pages out there do have tiny memory leaks. But if you have bigger ones, they can really add up and can lead to your page becoming slower or to actually even crash in the worst case scenario. Now, it's also interesting to think about different ways of solving one and the same problem in JavaScript, so to find code alternatives with better performance. I will show an example for this throughout this module. In the end here, this is related to the first box here in the runtime performance part, the code execution which we want to optimize. When you, for example, loop through an array, it turns out you have a couple of different ways of doing so, and they don't all have the same performance. So that's also a thing you could think about and you could try to optimize. Related to that is another approach which is called micro-optimizations. You can optimize certain parts of your code, and actually looping through an array with a quicker alternative would be one example for such a micro-optimization. You can optimize parts of your code for specific use cases. You could opt to use a certain data structure because it's a bit quicker than that other approach you used before. Now, generally, you want to shy away from such micro-optimizations though. And we'll come back to those throughout the module and explain why you should be really careful when you try to optimize everything. But it is a thing which can matter in niche scenarios and very large applications. The most important parts you want to care about are the first two boxes here in the runtime performance part, and of course all the boxes in the startup time performance part. And of course, as mentioned, always keep in mind that JavaScript is just one part. When we talk about optimizing our web page, it also includes things like writing efficient CSS and so on, but that's simply not the focus of this course, and JavaScript typically is the most important thing to optimize. So with that, we're almost done with the theory. Let's now find out how we can approach this whole performance optimization thing. Now, when you want to optimize your page, it's actually wrong to just go into the code and start changing anything. Instead, you want to measure and audit your page and find performance bottlenecks. Don't guess, instead measure. You want to find out how many round trips you have, how big your script is which needs to be downloaded. You maybe want to set certain budgets so that you know, okay, my script has to be below 100 kilobytes, and if it is above it, I will do everything I can to shrink it. So that's of course one important thing, and you want to find out how big it is and how long it takes before you start optimizing it. You also want to measure the runtime performance with the help of browser dev tools. There are a lot of useful features in modern browser dev tools, which you can use to find out how long certain parts of your script take, and then you can find out if that seems too long to you. You can try out an alternative and find out if that is actually better. You can also explore best practices and patterns and benchmarks you find on the internet. You will find a lot of blog posts and discussions when you Google JavaScript performance or even more specific performance questions. And you can then have a look at how other people are solving certain problems or how they are approaching certain things. So this can also be a useful thing to find out what you could look into. And also important, because that is a common mistake, when you do measure performance, measure your production-ready code. Don't do this in development mode, because in development mode, your code is not optimal at all. Build tools like Webpack, where you use the Webpack dev server. Inject a lot of extra code into your code to enhance the debugging experience. Now, that's great for finding ordinary issues and problems, but it's not great for measuring performance, because the performance during development will not be that great, because it's simply not what matters during development. But you want to, of course, have great performance in production, so it's the production-ready code you should test. Now, when we talk about measuring performance, there are a couple of different ways of measuring it. Now, I mentioned the browser dev tools. You also can add certain code snippets to your code. To be precise, you can use Performance Now, which is available in the browser, to get a time snapshot, and you can take that before and after you're running an operation you're not sure about. And this allows you to find out how long an operation takes. Then, of course, outside of your code, you do have the browser dev tools, as I mentioned, where you have many features that allow you to detect all kinds of different problems and bottlenecks you might have in your code. And you also have certain websites like jsperf.com, which allow you to benchmark certain code alternatives against each other and find out which one is quicker. You also have webpagetest.com, which is a site you can use to test a hosted website. So not your locally running one, but a hosted website, which then will give you a rich report on how that site performed and, what you could look into there. Now, these are just some tools, and I can only recommend that you also Google website performance, JavaScript performance, to find more approaches and more tools that might work well for you. So let's now dive into a concrete example. And attached you find a basic project where I give you some JavaScript code I wrote and a dist folder with an index.html file and some styles, and also 2 Webpack files and a package.json file. Download and extract this attached project, and then in there, open it in your editor, open the terminal there, and first of all run npm install, of course, to install all the dependencies this project needs, which are simply all these build tools like Webpack. Thereafter, you can run npm run build dev. Now, I told you to measure production performance, and we will do so later, but just to see what we got, let's spin up that development server for now. So this will now open that development server. And once you visit this page, you will find this basic application here. Now, important, visit this page in an incognito tab so that you have no other plugins or browser extensions interfere with your code. And what you got here is in the end a basic site where you have a bunch of dummy products. You can also add a new product here, and it will be added at the top here, as you can tell. And you can then also delete a product here and yeah, interact with your application like that. So it's a very simple project here, very simple website. Of course, all the interactions you saw here are driven with the help of JavaScript here. So here we have 3 script files, which in the end make sure that what you see on the screen, well, works the way you see it. Now let's see how we could approach optimizing this app here. And of course, it's also important to realize that this is not a slow app. It has no huge performance issues, as you can tell. Everything works quite smoothly here. Now, of course, because I'm on a fast device here, I have a fast internet connection, but also in general, because even though I added some problems to the code here, it's not horrible code, and it's also not that large of an application. But issues like the ones I added here could add up in a bigger application, and therefore fixing them, as we're going to do it throughout this module, is a good idea. Now let's first of all have a look at how we can analyze this application with the help of the browser DevTools. And there are a couple of things we can have a look at there. Now again, keep in mind, this is the development mode code, and therefore it's not fast, it's not optimized, but to walk you through the different tools we have, it is of course fine to use. Now one tool we can use to find out how often we interact with the DOM and what we affect in the DOM is the Elements tab in the DevTools. And here I'm talking about the Chrome DevTools. Most browser DevTools have similar tabs or tools built in, but Chrome has really great development tools, and therefore I'll use it for this section. So the Elements tab here is the first one. Now let's reload this page and let's have a look at one example. Let's expand the unordered list here so that we can see all the list items here. And now watch the list items here on the right, not on the left, but on the right. When I click delete on a carpet, watch it on the right. You see, these items all were highlighted. Now Chrome highlights the items here which actually were touched by it, so which were changed or which were added or re-rendered. And of course, this already gives us one hint at something which might not be perfect at the moment. When I delete, for example, the last item here, the t-shirt, it's a bit unexpected that all the other items are changed as well. So maybe that is something we can optimize. Now we got other tabs which are interesting as well. For example, the network tab. Here we can find out how much code we're downloading, how long it takes, and how many round trips we have. So if we reload this starting page, here we see we have a couple of requests. Now, the last 2 requests are only related to our development setup. They will not be there in production mode. The first 3 requests are always there because we have our HTML page, we have some CSS code, we have some JavaScript code. Now, this code is not optimized at all. Instead, it has a bunch of development-only code added to it, and therefore you can tell these files are quite large, especially the JavaScript file. It has a size of over 1 megabyte, which is really big. So that will be smaller in production, of course. Now, since I'm already using Webpack here, what we don't have here is extra HTTP round trips. I am using multiple files here, and I do import them into each other, but since we have Webpack here, they are actually bundled together. So Webpack ensures here that we don't have too many round trips. So we already have this optimization. The size, again, will not be bad in production mode. In development mode, of course, it is an issue, but we will also optimize this for production mode, because in the production mode Webpack config, the mode is set to production, and this will lead Webpack to shrink our code and optimize it even more, as we will see in a second. So here we have no huge issue, but I still want to show you an issue we could have if this 1 megabyte code would be our final output. It isn't here, but imagine it would be. Because here in the DevTools, you can do a couple of interesting things. First of all, make sure you disabled cache here in the network tab so that the browser doesn't cache as long as you have the DevTools open here. And then here, on this dropdown where you see online, you can throttle your internet speed. For example, here we could choose slow 3G to simulate our slower network speed. And if we do that, you will see this now reloads and it spins and spins here. And now you see When I click this button here, I get errors here. This is not an interactive page. We see something, but I'm not able to do something. I actually reloaded the page here because JavaScript was missing. JavaScript here prevents the default, but because JavaScript is 1 megabyte big and we're faking a slow connection, it takes too long to download JavaScript, and therefore our application is actually even broken because this button isn't handled correctly. So here we already have an example of why a too large script file could be a problem. Now again, here it actually isn't too big. This is just in development mode. But if that would be your production-ready output, you would want to do everything you can to shrink it. So here I'll disable throttling. I just wanted to highlight what the problem can be here. So let's move on. What else do we have? Well, we have the Performance tab, which sounds important if we talk about performance. And there you can also do this throttling. You can also do CPU throttling here to simulate a slower CPU. For example, if I set this to 6 times slowdown, by the way, you can open this menu by clicking the gear icon here in case you don't have it yet. If I set this to 6 times slowdown, we could check whether our app now is a bit slower. Now this page here actually still is pretty fast because it doesn't have that complex of a script on it. But if you had a page with a lot of complex animations running or a lot of complex interactions, then you could use CPU slowdown here to check whether it might have issues on slower devices. The Memory tab allows you to do more things than just throttling though. You can record performance here and then analyze it in detail. So for example here I'll turn on throttling, now click that record button, click on delete on any item and click on the record button again or click on stop down there. Now what you'll get is such a profile here. And you see there's a lot on the screen. So what do we have here? Now for one here you see screenshots of the app over time, so you see how it changed. You see that here because I have this screenshot checkmark here. You could of course remove that to not take screenshots. You could also show a memory timeline so that you can see memory consumption. This can be helpful for analyzing memory leaks, but for the moment we don't need it. And then you have all this part here. What is this all about? Well, this is the timeline of the snapshot you captured in the end here. Now here you see the work that was done, and at the bottom, if you increase this here, you see a breakdown of the overall work. And you see for the entire snapshot I took, most of the time it was not doing anything, which is good because that means it is able to capture user input. You see that around 100 milliseconds were taken for scripts to run, and then we had some rendering on the page going on, some painting, which is in the end related to rendering. So these steps together are basically which bring something onto the screen, and some system work, which also was done. Now, of course, the exact numbers will be different for you. Now we see here in the timeline when which tasks were executed. For example, back here, we have nothing going on. Nothing is going on here. And you can simply press and hold to drag here and select a part of that screen, which is then zoomed in here at the bottom. For now, I'll not zoom in, but just increasing this again. Now we see some work is going on here, right? So maybe we zoom in this part by simply holding and dragging and leaving go. And now we zoom in here in this detail analysis at the bottom. Now what we see down there are a couple of things. We see the frames per second we had here. We see user interactions, for example here that we had a mouse up event because we clicked on a button. And we have the main thread. And you learned that JavaScript runs on a single thread. Well, that is that thread on which it ran. And there you see that JavaScript ran because we had a click event to which we listened. And we also see that here already we have a problem. This is marked in red by the DevTools here for me because the handler took 92.26 milliseconds, which is quite long. We then see that because of the click, a function call was triggered. And if you click on it, you even see in which file this function sits and which function it was. So you can find out which function executed there. Now you can then have a look at this by scrolling down here on the y-axis to see the call stack. You see that the delete product function was called. You see that it took 6.4 milliseconds. By the way, you always have a total time and self time. Total time simply is the amount of work this function took and all the other functions that were called inside of the functions took. And self time is the time this function took without the work of the included functions. Generally, it's the total time that matters to you. So we have delete product. This in turn called render products, which took 6.4 milliseconds. And then here we can zoom in even more with the mouse wheel. We see that an anonymous function was executed there. Append child was used. We see that we seem to reach out to HTML here. The small blue bars here, that's when we reached out to HTML. We parsed our HTML code. So we probably interacted with the DOM here in the script, and so on. So you can really dive into that and see how long operations took and how long a problematic operation overall took. Now, of course, you should always keep an eye on the overall operation, because here we have 100 milliseconds, which is not great, but of course, which is still relatively quick. Nonetheless, this might be one thing we might be able to improve, though you should keep in mind that we're still in development mode, so this is not really what the users will have in the end. So I'll turn off throttling and now move on. This is the performance tab, and I'll give you further resources to explore everything you can do here in the lecture after this one. First of all, let's move on to other tabs though. And there, for example, we have the memory tab. The memory tab allows you to take memory snapshots. And here the heap snapshot is the most interesting one. You can take a snapshot by clicking on Take Snapshot at the bottom here, or on this Take Snapshot button here. Now, if you take a snapshot, you get such a memory snapshot, which looks very, very complex. In the end, this gives you everything, shows you everything which is stored in memory because of your web application. And there are a lot of things in there the browser manages automatically no matter what you do in your scripts. Now, diving into this snapshot here is really, really hard. More interesting is to see comparisons between snapshots. For example, here I took a snapshot. Now I will delete the item and take another snapshot. And now if we go to the second snapshot, here on the summary dropdown, we can use comparison. And this gives us the difference between this snapshot and this snapshot. And if we have a look at the comparison here for the second snapshot, we now see which items were added to memory and which items were removed. And for example, here we see that what was removed was a button element, a heading, so a H2 or H1 element, a list item element, and a paragraph element. And these are all the elements which are part of such a rendered product. You see the delta here compared to the previous snapshot is -1, which means in the end, effectively, one element was removed. And this is good. If this would not be the case after deleting a product here, we would probably have a memory leak, because that would mean that we still have the item lingering around in memory somewhere. And I'll come back to memory leaks later. I just want to show this tab right now. It will become more important later once we analyze our app for memory leaks. And last but not least, you have this audits tab here. There, for example, you can run a performance audit. You can tick different boxes here. At the moment, we're just interested in performance. And then the browser, Chrome, will do a couple of checks for you and find out how your app behaves. For example, here we can run the performance audit, still in development mode, so not optimal. And you see in development mode, we have a pretty poor performance. We have a slow loading time. First contentful paint is in the end an indicator for when our app is putting something onto the screen, when it is interactive, and so on. You see the different screenshots for the timeline, and you get some opportunities here. For example, that our scripts are too big. So this can be nice to get a general idea of which problems your page might have, and thereafter you could dive into the more specialized tabs to find out what exactly the problem is and what you can do here. So now, after this general round trip here, let me point you at some other resources before we then test this under production circumstances and have a look at some potential improvements. The tools built into Chrome, which help you with performance, can be really daunting. They can be very complex. And therefore, it's important to know where you can learn more. Now, attached you find two important pages which I can only recommend. One is from the Chrome website in the end. Here, a deep dive into the performance analysis tools in the browser DevTools. Here, you'll learn everything about these tools, what you can do there, what everything means, how you can configure it, how you can save and load snapshots, and so on. So this is really useful and absolutely a resource I would recommend that you dive in if you want to learn everything about these tools and you want to be able to analyze everything. Also check out the other resources here, like this article about optimizing website speed, which is about more than just JavaScript. It's also about optimizing images and so on. And all the other articles here about performance and JavaScript. You can also learn more about the browser DevTools in general on this page. Also interesting is this other page which you find attached. It's about web performance optimization in a browser context. Some concepts here can also help you with Node.js, but most concepts here are targeting the browser, just as this first article, by the way. And this is really the part where performance optimization is most important, or where you have many opportunities of messing up stuff. So this second article here also gives you more insights on how to measure performance. And then it also gives you this loading, this startup performance, and how you can measure that and what you can do there. And the runtime, the rendering performance, with some ideas on what you could do here, what you can keep in mind. Also outside of JavaScript, when it comes to optimizing animations, which are controlled by JavaScript and CSS, for example. So these can be additional resources that are helpful, but with that, let's now dive into our application. Let's test it under production circumstances and have a look at some things we could optimize there. So let's dive into our code, and as I mentioned multiple times, let's test it under production circumstances. So here in my terminal in the editor, I'll run npm run build prod, and this will build it for production. Now, the problem we have with that, of course, is that now we built this, but now we have no running dev server. Now, we can, of course, use a development server like serve, which we used earlier, and manually navigate into the dist folder and then run serve there if you still got that installed to run that, but it's not the approach I want to use. Instead, here, I will tweak the webpack.config.js file and set my mode here to production, actually, to make sure that this is optimized and we do have our production environment. But at the same time, I want to make sure that we use a dev tool that gives us source maps so that in the browser DevTools we can map our optimized code back to the original code, which doesn't bloat our code. Because most source maps, when you add them to your code, they also affect the size of the code. But thankfully, Webpack also has an option we can choose here, which gives us a source map with all the features we need without affecting our code size. It just takes a bit longer to generate that, but here that's not a problem. We got time. So what we want to use here is now just source map. Now if we run npm run build dev again, we're using this configuration, which now actually builds for production, or it simulates production, but which also uses a dev server and gives us source maps so that when we analyze our code in the DevTools, we can still find out which parts of our original code are responsible for that. So now with that, back here in our application, if we go to the network tab, we clear everything there and we reload, we see now shop.js is much smaller, as you can tell. Now, I will say it's still not exactly on the same level as the fully optimized code. Just to quickly also show that, if I would run npm run build prod to use my other Webpack config, where I also build for production, but where I use a better source map, which is smaller and doesn't add anything to the files, or almost not anything. If we use that and we then go into the dist folder, and there I use that serve package which we installed earlier in the course. If I now visit the server, the host spun up by this serve development server, and there we inspect the network tab, you see we only have 9 kilobytes. So this is actually what we will have in the end once we ship this to a server. It's also gzipped, so compressed by our server we're using here, and therefore it's even smaller. That is something you set up on the server side though, so that's such a server-side configuration optimization I was talking about, and you'll find an article, a text lecture, with more resources on how to configure your server and what you might want to keep in mind there later in this module. Still, for our purposes here, this should be fine using this in-between solution, though if you want to do it perfectly, you would actually use the real production build, but then you don't have source maps. So if we would use cheap source map here in the other Webpack config file, we should achieve something similar. We still might have some overhead because of our Webpack dev server, but it should be closer to the final size. But debugging or finding problems in our code would then be harder. So I will go for this in-between approach and run npm run build dev with this adjusted Webpack config, which is closer to the production result. So here we got this size here, which is okay. And now with that, let's in general find out how we can analyze this app and improve our code. So now what can we do here? How can we optimize our startup time? Size is okay, especially keep in mind, it will be even much smaller later. We're not having multiple round trips. Now one thing that could still be interesting is to check how much of the code which we download initially here is actually being used. Because if we have a lot of unused code, then we might be downloading too much here. We might be downloading code which we don't even need yet. Now, thankfully, Chrome helps us with that. If you press Escape here in the DevTools, in the Network tab, then this bottom tab here opens, and there you'll have a Coverage tab. Now, in Coverage, you can check how much of the JavaScript code is getting used. Click on this Instrument Coverage button here, and it will tell you how much code is unused. And in this example here, you see around 41% of my JavaScript code is unused. Now, if we click on that, you see here at the top this opens. And there you have a green line next to code which is being used and a red line next to code which is not being used. Now, this here is our code as it is produced by Webpack. So therefore, here we also see code which is actually injected by Webpack, which we didn't write. So there will have little influence on whether we need it or not. You can go to the Webpack folder here in the Sources tab, there to the dot folder, and there you will find your source non-optimized folder, and in here you find your original files, and also there you see if code is getting used or not. And what you see here, for example, is that a lot of the code is getting used, but for example, in product management, delete product, all this code here is not really getting used. Add product is also not getting used, which means it didn't execute yet. And here in rendering.js, we also see all that code is not getting used, though that is actually not correct. This is not detected correctly. You see it detected that the for each code was used. Therefore, actually, this code did execute here. So that's not displayed correctly. But indeed, what will be true is that, for example, delete product did certainly not execute yet because we haven't deleted any product. And the same for add product. We haven't added any product, so this function wasn't used at all. Or to be precise, the code in there didn't execute yet. The function itself is actually used because it's referenced in shop.js, where I have an event listener which points at add product. So that is getting used here indirectly, it just didn't execute yet. Still, such unused code is an opportunity for improvement with the help of lazy loading. So this import syntax where you only import a file and download it when you really need it instead of upfront. So let's do that. Let's add such lazy loading here to make sure we use more of the code which we initially download, or put in other words, that we download less code initially. So back in our code, we see in the end we're pointing at add product here, but as long as the user doesn't click the button here, the add product function in the product management file is not getting executed. Same for delete product. As long as a button wasn't clicked, this is not getting executed. So how could we improve this then? Well, we can go to shop.js, for example, and there maybe up here. We could add an add product function here instead of importing it from product management. And add product in the end is a function. Here I'm using an arrow function. Of course, we could also create it like this. So it is a function which will receive an event object because we bound it to the submit event here. And in there, I now want to call import as a function, which you'll learn about in the modules course section. This is supported in JavaScript and also by Webpack when it analyzes and bundles your code. And here I want to import product management.js. Here you need to add this extension. And this gives you a promise. Of course, we could use async await too. The promise will give you the module, and I'll just name it mod here. And this module will have, or this module object will have everything this file exports. So in our case here, we would call add product then from this module when we eventually imported it and forward that event object. Now, this theoretically should only load this code when we need it, but keep in mind, I'm still importing something from up there, which always gets imported. So the whole file has to be loaded anyways, because I need one function from it. Not all functions, but still a file can either be imported entirely or not at all. So if I reach out to init products here in this shop.js file, then this whole product management file is getting added to my bundle. And whilst this won't break the code, it will also not really help. So if we save here, and this compiles and we reload, you see in the end here, if I try to add a product, this works, but we certainly didn't gain anything. Instead, we just actually added more code. But maybe we can optimize our code. We could add a new file, and for that I'll actually create a new folder, optimized, so that we can see the difference in the end. And I'll bring over these files here. And in the Webpack config.js file, I'll now switch to optimized, which should get imported. Same here in the production Webpack config file. Entry point is in the optimized folder, and then restart the dev server. And now in the optimized folder, we could add a products.js file. And in product management, we can grab the products here, put them into products.js, and there turn this into a const and export it, so that now in product management, I can import products from ./products. And I'll actually import it as prods, so that here I can also create a new variable here, products, which holds prods here. So that when I use products and set it down there, this still works, because that now this is a variable in this file initialized with the data from this file. Now, why did I do that? Why do I store products in a separate file? So that I can now grab this init products function here and remove it from product management and actually add it to shop.js, which is where I'm running this function. So here we can add this init products function. And now we just need access to render products and to products. So we can import products from ./products and import render products from ./rendering. We also pass a delete product thing to render products. And if we have a look at our code, we find out that the delete product thing here is actually a pointer at the delete product function here. Because inside of the rendering function, when we create all these products here, I add a button where when we click on it, I want to execute that delete product function. So a pointer to the function that should be executed upon such a button click is received by the render products function here in the rendering file. And therefore, whenever we call render products from anywhere, I need to pass a pointer at this function. Now that's a problem in shop.js because delete product is a function defined in product management, and I'm actually trying to get rid of that import. Well, we can do the same thing as with add product. Here, I'll just name it delete product, import product management dynamically, and then there call delete product. Now, delete product, when being called, needs to get the prod ID of the product that should be deleted. So here I expect to get that product ID as an argument so that I can forward it. And then here, when I pass delete product to render products, we're all good. Now, if you're wondering where this ID is coming from, well, I'm passing a pointer at delete product to render products. So inside of render products, this ID has to be passed, and indeed it is. So that will work. Now with that, we can remove the product management import here and fix that typo. And now we got rid of that extra import. Now let's see if that helps us in any way. If we now reload, you see our code here shrank a bit. It's 1 kilobyte smaller. Of course, because we're talking about very little code here, which we shifted around. So the majority of the 168 kilobytes you see here is still development mode only code, which is why we didn't see a huge change. But it got a bit smaller. But what you will also see is that if I now delete something here, now you see the extra files are getting imported. Now, arguably, they're bigger than what we removed, but this is just an example of how you could split your code. For a tiny application like this one, this here all is probably not worth the hassle, because Webpack has to add some overhead code because of this, and therefore we might actually end up with more code than before. But it shows you the general way of thinking. And if you had more code which you import dynamically like this, if add product or delete product in product management were more complex functions, then you could save a lot by only importing them dynamically when they're needed instead of importing them up front, which we're doing at the moment. Now, in case you wondered why 2 files were imported when I click delete, keep in mind that my 2 dynamic imports here are both pointing at the same file. So as soon as I need one of them, both actually get added. So with that, we had a look at the startup time optimizations, though again, just to emphasize it here, because of the simplicity of this app and the code here. Of course, these optimizations are a bit redundant here, or might even lead to slightly more code being downloaded. The bigger your application is, and the bigger the chunk of optional code you have, the more useful this will be. What I can show you though, if we reload, is that if we have a look at that coverage thing again, so I'm reloading here, take another coverage snapshot, you see here we improved a bit. We're down to 35%, so we have less unused code now. Indeed, if you inspect this all now, you see in rendering, this now is detected correctly actually, that's great. So here we use everything. In products.js we use everything, and in shop.js only these functions haven't been used yet, but this of course is not much code. Everything else is green. So we have less unused code, and therefore we definitely improved that with the help of lazy loading. Now let's see what else we can do besides the potential startup time improvement we had a look at here. So we potentially at least improved our startup time. Now let's have a look at runtime performance. And for that, I'll go to the Performance tab here, enable CPU throttling, clear all previous snapshots, and I'll take a new snapshot when I delete a product. Then stop that. Now, you see, here's the interesting part, so let's zoom in there. You see ongoing network requests. That were the extra chunks that were downloaded. Let's close that. Let's have a look at the main thread down there, because that's the more interesting part. Now what you see is, here I got my click on a button, and you see we have a little warning here that this took around 80 milliseconds, which isn't great. We have the function call, and then we have another function call here, where other functions are getting executed based on the extra bundles we added. Now here, whilst we don't see the function names, unfortunately, here in this tab, we see it's from line 10 in shop.js, and this is the delete product function, which makes sense because that is what should be triggered if we click the delete button. And then after our extra chunks were downloaded, more code was getting executed here from our, well, extra chunk files. Now, to be honest here, this time it took for the handler, we probably won't be able to do much about it because the function call here, which is getting executed, which takes some time, really isn't taking that long because of any of our code. You see all the code which is executing here and executing here runs fairly fast. I mean, for example, this entire script here takes like 42 milliseconds, which should be okay. But actually in our script, we still have an issue or a couple of things we can improve. For that, I'll even turn off throttling because I can show it nonetheless. Again, hit escape here, and then in the bottom tab here, click on rendering and turn on paint flashing. This will allow us to see which problem we have on this page. You can now close that. If you now reload, you see everything flashes green, and whenever something is re-rendered, it flashes green. Now the interesting thing is, if I delete, let's say the last item, the t-shirt here, so if I click on delete here, you see everything here flashes green. And that's what we saw earlier already. If we expand the unordered list here and we watch the list items on the right, whenever I delete the item, everything here is updated. The entire unordered list and all the list items. And now I'll turn off the flashing because it's a bit annoying. But you see the problem here. The whole list is being re-rendered whenever we delete an item, even if it's the last item. And there is no reason for that to happen. It makes more sense when we add a new item, because when we do add a new item, we actually add it at the beginning of the list. So of course, JavaScript has to shift all items to the back, or the browser has to shift all items to the back here. But why is it re-rendering the entire list when we delete an item, even if it's the last one? Well, we can see the answer if we have a look at the rendering.js file here in the optimized folder. In rendering.js, we see render products, which is the function responsible for displaying the product on the screen. When it executes, it always clears all existing DOM elements in the product list element, which is in the end that unordered list element here with the product list ID. And then it creates all these new DOM nodes and adds them for every product we have. So for 5 products initially, if we had 100 products, it does it for 100 products. Now this is really not a great code here. This is not what we want to do. Re-rendering everything for every change can be horrible. Imagine you have a list with 100 items and you delete everything on the screen and re-render it all for every tiny change. Well, if your users have a bit slower devices, they will probably feel that and see that, and it's not a great user experience, because accessing the DOM in general is quite performance intensive, and such errors like this one can quickly add up. So we should improve the render products function here to not re-render everything whenever we change something. And therefore, to improve this, I will actually add a new function here, update products, which should be a little bit more careful when we add or remove an item. We will still need render products to render the entire list when we initially render all products here in init products. But I certainly don't want to call render products when we added or removed the item. So I'll leave render products as it is, but in update products, I want to add code which we can use when we added or removed an item. So therefore here, I expect to get the product data which was added or removed as a first argument. Let's say we also need the product ID in case we're deleting, so that we directly get that. I want to get that delete product function, because if we add a new product, I will still need to render a button which points at this function. And I want to get one last argument which tells me if we're calling update products because we're adding a new one or because we're deleting one. Because then I can use an if check to find out if we're adding. And if we do, I essentially want to create a new product again and append it. Otherwise, I want to remove it. So let's start with removing maybe, in the else case here. I want to get access to my product element here, or product L, to stay in line with the naming and other parts of this script, by using document get element by ID, prod ID. Because when we render a product in the future, I want to add the ID attribute on the rendered DOM node and point at the ID of the product which was added. So here in render products, my new list element, which is my new product item here, should actually get the ID property set to product.id, so to the ID of the product we're rendering, so that every DOM element has the ID attribute, which is the ID of the product. We can then use this to get a hold of that element when we want to delete it. And then we can call product element remove, or for better browser support, of course, as you learned, reach out to the parent element, and they are called remove child on product L. Both works. I'll use the shorter, more modern approach here, which doesn't work in all browsers though. So this is now the deletion part. Now I want to call update products when we do delete. So in product management, in delete product, I don't want to call render products in the end, but instead update products. So from rendering, I'll import update products. And down there, I call update products with a pointer at the product I want to update, the ID of that product, a pointer at the delete product function, so at this function itself, and the value for isAdd, which here would be false. Now the problem is the product which is affected, I don't have access to it here. And this code here in general also isn't optimal yet. Now we can optimize this code later. For now, I'll add a variable deleted product, and here in this loop where I go over all my products, I'll check if the product I'm looking at does not have the ID of the deleted one, which means I want to keep it, which is why I added to updated products, which I then set as my new products array. So else, if the IDs do match, I know this is the product which was deleted, so I'll set deleted product equal to prod in that case. And then down there, deleted product is what I want to forward here. Prod ID, which is the argument I get here, is the ID I want to forward. Here I point at the function itself for this argument, which the delete part of the update products function won't even use though. And important, for isAdding, we set false because we're not adding, we're deleting. So now when the delete product function executes, update products should actually execute, and that should now update our list of products in a way that doesn't cause the entire list to re-render. Well, let's test this. Let's reload and expand unordered list here. Now you see the IDs are being added here. I'm using dates as IDs here. And now watch the list items on the right when I delete the magic broomstick. You see, the list items here didn't flash, only the unordered list, because the unordered list of course was affected, one of its child items was removed, but the other list items which weren't removed weren't re-rendered, they weren't touched, and therefore this is far more efficient than what we had before. Now definitely use this now as a chance to pause and try coming up with an approach of implementing adding in a way that doesn't affect everything or doesn't re-render everything. Of course, in the next lecture, we'll also do it together. So now what about adding a product? Well, when we add a product, we obviously want to, create a new product and then add it to the list, but we want to add it to the list in a way that doesn't affect the other product items so that not everything is re-rendered just because we added a product. So therefore, when the mode is adding here, I want to create a new item. So basically want to execute this code here, though I will say we can optimize this as well. But then I want to add it to the list in a way that doesn't negatively impact the other parts, that doesn't re-render everything. So first of all, let's outsource this create element code here so that we can reuse it by grabbing all that code inside of that for each anonymous function here, like this here, without the product list L append child code, and add this to create element. Now in there, we'll need a product argument. We'll also need a prod ID, and all the places where we access product.id, let's use prod ID instead. And we'll need a pointer at that delete product fn, that delete product function, which I'm using here. Now we can call create element, and this function should also return something. It should return the new list element, the new product element for the DOM, which is created here in the end. So now we can call create element, call it here in render products. There we have our new list element, which is the result of calling create element with product, product.id, and delete product fn, which is an argument we're getting here, which I'm just forwarding to create element. And now here in update products, we can also call create element, forward product and prod ID, forward the delete product function, and what we get back is our new product L or new list L. Of course, we can use the same name as up there, just using a different one to avoid confusion. And now we want to add this to the DOM. And actually, we want to add it to the DOM such that we add it in front of the other elements, because the logic we have in product management for adding a product is also that we unshift it, so that we add it at the beginning of the array. So we should reflect this also in our rendering method. So here, I now need access to the place in DOM where this should get rendered. And I can get this here in the same way I'm getting it in render products. It's that element with the product list ID. That's in the end the unordered list. Now, since I need access to this both here in render products and in update products, it makes sense to outsource this and turn this into a global variable here. So now with that, when we use product list L, like we do here in render products, it will still be available. And now we can also use it here in update products. Product list L, and now insert adjacent element after begin to add it inside of the unordered list, but at the very beginning of it, we want to add the new product element. And now we just have to make sure that we call update products from inside the product management file when we add a product. So here at the moment we call render products. This is not what we want to do. Instead here in the add product function, we want to call update products and forward the new product we created, the new product.id, so that we also pass on the product ID in a dedicated way. The delete product function pointer pointing at this delete product function here. And also true for is adding. Another implication of this is now that we can remove the render products import here, because we're not needing this here anymore. And with that, if we now save that, we should have a setup where we don't re-render everything if we add an item either. So let's again have a look at all the list items here on the right, and let's add a new product here. And if we click add product now, okay, this actually reloads, because in shop.js, where I have my dynamic import function here, we should call event prevent default here. Otherwise, when we call it in the real add product function, this will be too late, because this happens asynchronously after this extra script was downloaded. So we need to do it here. Little oversight from my side. Sorry about that. It also means we can remove event prevent default here in product management.js in the add product function. But now with that, let's try it again. Let's now enter test 5 here, or whatever you want. Watch the list items on the right and click add product. And you see, this first one flashed, the other ones didn't, because they weren't re-rendered. So now with that, we actually implemented a huge improvement. We might not really see it here in performance because of, well, the simplicity of this app, but still, this is something which can really slow down bigger apps if you're doing it wrong. So let's now delete something again here and take a snapshot of that. Well, as you can tell, if we expand the main thread here, we didn't gain that much here, but actually it's a bit faster than it was before. We could speed it up a little bit at least. And I can tell you that this is definitely better than what we had before. And still, it's not optimal yet. Our rendering code isn't perfect yet. We're creating a bunch of DOM nodes separately, and we can actually do this with less code and with a bit better code. So let's revisit the create element function here. Of course, we need to create our list item element here, but the h2 and the p tags, we don't really need to create them like this. Instead, what we could do here is we could reach out to the new list element and set its inner HTML here to a template literal like this. And then here, then add a h2 tag and paragraph tag. And then here we dynamically output whatever the user entered. So in this case, the product title, and then here also the product price. Now beware of cross-site scripting attacks here. As you learned in the security module, you want to sanitize this content normally. Here we're not doing it, and the user could therefore inject malicious code here. So this is a security issue, and you normally want to sanitize it therefore. I'm just not doing it here because I want to focus on the performance part. I will create the button like this because there I will also add an event listener. These two lines can go now. They were related to the previous way of creating separate nodes for the h2 and the paragraph tag. For the button here, instead of setting inner HTML, we can also use text content, which is a bit better because we are only setting text here, so no need to use inner HTML. Adding the event listener like this is fine. And then down there, we don't need to add the title and price element anymore because we're using inner HTML. Instead, we just need to add the button at the end. So this is now actually a better version of that snippet. It's less code and, well, simply a bit better. With this now, I'm quite happy with our rendering code here, and you can definitely always find something which you can improve. But for now, this is good, and the part where we made sure that we don't unnecessarily re-render the entire list is of course the most important improvement we achieved here. In this dummy application, which I'm giving you here, we now actually already achieved the most important improvements. Now there are smaller things where we could consider alternative code, which might be better, though here we really also get closer to these micro optimizations, which you generally want to avoid, and I'll come back to them and why you might want to avoid them in a second. Let me show you one thing or one part of our code that we could improve though. For example, here in delete product. This code for deleting a product, we can improve it, and for performance, we might gain a little bit, but we can at least improve it for simplicity reasons. Because what we're doing here in the end is really a complex way of overriding our products array with a new products array, which of course also therefore is stored in memory and occupies some space there, when we don't really need to do that. Instead, what we could do here is we could simply use the products array we're importing. Arrays are reference types, so when we work with the imported array here, we work with the one array which is set up and stored in memory here. And instead of overriding it with a new array of products, we can just get the index of the item which should be deleted product index. For example, by using products find index, looping through all products here in the anonymous function and finding the product where the ID is equal to prod ID I'm getting as an argument. And then we can reach out to product, so to our array, and use the splice method you learned about in the arrays and iterables section to splice the element at this ID and only that element. And this would be a simple way of updating our products here. Now I need to forward the deleted product here, so I want to store it before I remove it from the array, deleted product, by reaching out to products and accessing the item at the deleted product index. So now we store a pointer at this product here before we remove it from the array. Therefore, since we still have a pointer, it will live on. We pass the pointer to update products. With that, if we save that and we go back here and delete, this still works. But now actually here we have less complicated and probably also a bit faster code. Another improvement we could make is in add product, I'm always getting new access to title L and price L. Now since add product potentially runs more than once, we can also grab that, because these elements will always be the same, and turn them into module-wide global constants, which we can use in the entire module file here, because these items will never change. Also, when we select the items here, we have a bit of a too complex selector. This will work, but actually since every input here, and in the end I'm reaching out to my inputs here, has an ID. We have a title ID and we have a price ID. We can also just use document get element by ID instead of query selector, because it turns out that document get element by ID is a bit faster than document query selector. So here let's call getElementById in both places. Make sure to remove the hash symbol here, the hashtag. You don't need that when using getElementById. So now down to add product, we now of course can still retrieve our values here. We can still do our validation, create a new product and add it, so that's all fine. But now we improve this a little bit as well. Now you should be careful with such optimizations though. Now one thing which also costs performance, but it just is what it is in this app, is the fact that we unshift the array. Because as you learned in the arrays and iterables section, this simply means that JavaScript has to revisit all array elements and push them all, well, to the end of the array, because we add a new element at the very beginning. So all elements have to be moved. But it is just what it is. If that is what we want to do in this app, well, it is what we want to do. And that's the part where you should be careful when you try to optimize everything. It's easy to think in a super complex way and try to optimize things which really don't need optimization. Sure, using unshift is slower than using push. But unless you're doing this every second on an array with thousands of items, you probably won't notice a difference. Because when we talk about performance, sure, we might have a difference of, let's say, 10 milliseconds. But will this matter? No, this will not matter. So you should be careful when you try to optimize everything. It's often not worth it, and you might even break your app or come up with some strange workaround which offers a bad user experience, or which in the worst case is even slower, just because you try to avoid a certain way of doing something which just turns to be out the right way, even though it technically is slower than some other way. Let's dive a bit deeper into these micro optimizations though. I told you that you should measure before you optimize. Now thus far we haven't done too much measurement because the optimizations we did, mostly those regarding the DOM, are no-brainers. They are better, they're also not micro optimizations, these are really optimizations which can matter. Now here's an example for a micro optimization where we want to check if it's better. In rendering.js, in render products, here, I'm using for each. Now, this is not the only way of going through all items in an array, as you know. So let's find out if it's the best one. For that, let's log a start time with performance.now, which is a function that helps you measure performance. It gives you a timestamp in the end. And then here we have the end time, which is also performance.now, which I execute after for each. And then we can console log end time minus start time to get the time difference. Now let's save that and let's see what the time difference is. Open the console here, and you see here it logs around .33. And if we reload here multiple times, we see there are quite some differences, which already shows you that you have to be careful regarding such optimizations. You would want to run this a couple of thousand times by writing some extra script which just refreshes this or executes your script to find out what is better. So here we see we have a couple of different numbers, but we're somewhere around 30-ish, but really there is a lot of deviation. Now let's try a different approach. Let's comment out this approach, and instead let's use a regular for loop. Not even a for of loop, a very traditional for loop, where we have I, which starts at 0, where we then loop as long as I is smaller as products.length, where we then increment I by 1. And now let's grab this code here, put it in here. And here, of course, we have to access products for index I. And here it's also products I. And yeah, that should be it. Now let's save this. Now when you execute this a couple of times, you most likely will not see a significant difference. You might see some results which are faster. You might see less results which are on the higher end, as we saw it before. But there really is also a lot of randomness involved. As I said, you would need to run this tens of thousands of times. Well, turns out there are pages which do this for you. JSPerf.com is such a site. Now you need to log in with a GitHub account here to create your own test cases, which in the end are comparisons of different approaches. But you can also go to the popular test cases down there to find comparisons other people ran. And here I'm talking about JavaScript code comparisons. For example, here we have a comparison of 4 and 4 each. And you see a lot of other comparisons down there as well. Now this here is in the end a benchmark, which in the end has an array with a bunch of numbers, as you can tell. And then these different tests are being run. It tests going through all these items with a for loop, with a for off loop, with the for each function, and also with the reduce function. Now let's click on run tests, and now it runs these tests for a couple of times, and then it gives you an average. So let's wait for this to finish. And what you should see, and the exact results will differ, you can also run this for multiple times, but what you should see is that the traditional for loop actually is fastest. And if you Google that, if you Google for versus for off JavaScript and so on, you will find a lot of discussions where this is also discussed. Indeed, right now at least, the traditional for loop is faster than the for off loop, is faster than for each, and so on. Now, does this mean you should switch and replace all for off loops with this loop? Why did I even teach you for off if it's slower? Because when we talk about it being slow here, we have to be really, really careful. When we talk about a difference, like here in my browser, of 11%, that's not a lot. You might not be running across an array with thousands of items multiple times every second. If you do that, the difference might matter. Most of the time, in 99% of all applications, you're not going to do that. Because if you would do that, even with the fastest approach, it would probably be slow at some point. So when we talk about differences here, we really have to be careful that we don't go for the fastest result just because it shows it here, and totally forget that this doesn't matter in most cases. So when you're comparing results, if you're benchmarking and you're checking whether approach A is faster than approach B, for example, with benchmarking websites like JSPerf.com, you have to interpret the results with caution. Because of what I just said, that you might not be running thousands of operations and the performance difference therefore really will not make a difference, and then you should go for the code which is more readable and shorter and not for the most complex code which theoretically might run a bit faster. And in addition, keep in mind that performance is not a fixed thing. It might differ from browser to browser. Thus far we only tested in Chrome. In Firefox it might be a bit different, and it will change over time. Of course, if approach A is slower than B at the moment, this does not mean it's slower in a year or in 6 months. Especially the newer JavaScript engine features, which were added 1 or 2 years ago, will most likely become faster over time, and they might overtake the older approaches then. So of course you can then always go back to your code and re-implement it with the then best approach, or you keep in mind that you're not running this operation thousands of times, and therefore this micro-optimization really doesn't matter. So back in our code, this means we can of course run this loop like this, and it's nice to do that. It's also good to know how you can measure performance with Performance Now, but you shouldn't overdo it. And here, because it's a bit shorter, I will go back to my old for each approach, which isn't horrible, which is a bit slower, but again, we won't really feel that here. And therefore, this is the approach I will use here, and that is what you should keep in mind about benchmarking and micro-optimizations like this one, where you try to optimize everything, and you might therefore end up with longer or less readable code, or an approach which isn't the best anymore in a year or half a year. So let's explore memory leaks. Now for that we got that memory tab, and attached you find an article from the official Google Chrome developer tool documentation where you can learn all about that tab. And here one of the most useful things we can do is click on take heap snapshot to take a heap snapshot, then do some operation, for example delete a carpet, and take another snapshot and then go to comparison here in the dropdown to see the difference to the last snapshot. And this allows us to find out what changed in memory, which can be helpful for finding problems. So here, for example, we see a script element was added, which makes sense. That's the lazy loading going on. That's what Webpack does behind the scenes when we load the code for deleting. And yeah, other than that, a bunch of things were added. A lot of things which are going on here are really just not directly related to your code. What we can see is that, for example, when we talk about HTML elements, it doesn't look like we have a difference. It doesn't seem like we actually got rid of a button and a LI element. So that's not too good because we removed one, so it should be gone. Well, let's maybe run another snapshot and compare it to the previous one and see if we see a difference there, maybe by sorting for delta and looking at the things which got removed first. But even there we see what was touched is not really the LI element, the button element and so on, right? We had one deleted, but we also had one added. So it doesn't really look like we got rid of our element here with the current approach. If you click on that garbage icon here, you can also let the garbage collector run. But if we take another snapshot thereafter, well, we still don't see any differences, right? No matter how we order this, nothing was removed. So it looks like our LI elements are not getting removed here from the DOM when we actually delete items. So now let's see how we can find and fix this potential memory leak we have. For that, again, I'll take an initial snapshot here, then delete the item, take another snapshot, confirm that we still have that potential issue by having a look at my changes here. And here, oh, it now actually is gone. Now, you might or might not be seeing this. I ran this multiple times, and most of the time I didn't see this getting cleaned up here. Now it is cleaned up though. Well, let's give it another try. Let's clear these profiles, take a snapshot, delete the item, take a snapshot, have a look at the comparison, check delta, and we're back to where we were before. So let's have a look at the summary then, and there you can search for LI element and you'll find this HTML LI element summary here. If you expand this, you see a bunch of LI elements, more than we have on the page. We have 4, here I see 8. And now let's see if we can kind of find out which element here belongs to which element on the screen. For that, we can select the element here, and then at the bottom you have this retainers view. And here we see just a bunch of strange proto stuff. So this doesn't look like an actually rendered element here. Because if we go to the second one and we close this, here we actually see related elements or objects. And for example, we see a HTML button element, and if you hover over this, one of the buttons on the left should highlight. So this clearly is an element which is currently rendered. Let's go to the next element, close this, find the button, hover over it. Okay, this is the last element. So this also seems to be rendered. Let's check this element here, hover over the button. It's the second one. So let's go to this element, hover over the button. It's the third one. So we can say that these 3 elements here are currently rendered. They also all have the same retained size here on the right, which makes sense since they're all in the same state. We don't know what the first one is. Might be the internal constructor function, which JavaScript is aware of course, because if you create a new HTML LI element, JavaScript in the end will call such a constructor function, so that's probably what this is. And these 3 here, these are really just old objects lingering around, ready for cleanup. Here, if I see that, I also got a button element, but if I hover over this, no button is getting highlighted. We also see this has a greater distance than the other items. The distance in the end is kind of an indicator of how actively this is used. The smaller the distance, the more actively it's getting used. So this is clearly not getting used a lot. And the retained size is also smaller. So it's probably a browser thing that this doesn't get removed. It's probably not a mistake on our side. Now let me show you how a mistake and a real memory leak could look like though. Let's say for whatever reason we're keeping track of all the elements we're creating. So we have a constant, maybe here, rendered products, which should be an array, which exists in the rendering.js file. Now this is an array, and now whenever we add a new product, we want to add this here. So we have our rendered products, and there I push my new product L onto this array. We're maybe doing this so that thereafter we can console log all the rendered products we rendered in the past or we have currently on the screen. Now if I save this, we go to the console first of all. If I now add a new product here, we see this list item. If I add another new product, we see both list items here in the array. So that is working. However, if I now delete the item here, you will see that if I add yet another new item, the one which I deleted is also still part of the array. So we can already see that we might have a problem here. And I can prove that we have a problem if we go to the memory tab. Let's clear the existing snapshots and take a new one. And now let's delete this item and take another new one. Now if we go to comparison view, we still don't see that a list item was removed here. Now we had this before. But if we now go to the summary view and search for a list element, then we see a problem here. We see in the HTML li elements, we got a bunch of elements here, 10 to be precise, and there are some which are currently rendered. Here, if we hover over the button, we see which button gets highlighted. But we also see some, for example, this one here, which is currently not rendered. Now we had this before, but now this is probably not a mistake by the browser here, because we also find this detached HTML li element thing. So this is a hint that something seems to be wrong with our li element. And indeed we see it's stored in some array. So whilst this might be hard to read because there's a lot of stuff in there, we suddenly have a new element here in our list here, the detached HTML li element. And when we inspect it, it tells us that it's stored in some array, that some array holds a reference to it. So these are now indicators. Before we also had some li elements here which weren't cleaned up, but we couldn't find any issue in our code. Now here with this extra hint, we should take another look. And indeed, of course, here we have a memory leak. Every newly added item, every newly added DOM object is added to this array. Now, since I don't remove the items from the array when we remove them from the DOM, they are in a detached state. The DOM node was removed, the underlying JavaScript object wasn't. Normally, when you remove a DOM node, the browser also destroys the underlying JavaScript object. But if you have another reference to that object, as we do have it here, where we also point at that DOM object from inside an array, the browser, of course, does not delete the JavaScript object because it thinks you still plan on working with it. Well, maybe you do, but here it's just an oversight. What we should do when we really want to keep track of elements like this is we should try to also clean them up when we remove them from the DOM, for example, by ID. Or, of course, we just don't keep track of them at all. Maybe there is another way of achieving what we wanted to do. This is a typical example for a memory leak, that you point at elements in your code which you remove in the DOM, but which you then don't clean up in your code. And with the memory tools here in the browser DevTools, as you just saw, you can search for such problems. It requires some experience and trial and error, probably, but you can look for strange patterns and see if there is something you should check in your code which might not be entirely correct. And with that, we're done. Now let me briefly sum up what we learned. We had a look at runtime performance and potential improvements we can implement there. You should avoid unnecessary code executions, batch operations together, and avoid unnecessary DOM access, as you learned. You should, of course, also find and fix memory leaks, even small ones, because they can add up and make your page slower or make it crash. For high-frequency operations, you can compare different approaches, like the two for loop alternatives we had a look at, and use the faster one. And in general, you might consider micro optimizations, but you should also be careful about them because performance isn't a fixed thing. It can change in the future, and you might be optimizing for something which really doesn't matter. When we have a look at startup performance, then we want to eliminate unnecessary or unused code to download as small of a code package initially as possible. You also want to avoid using too many third-party libraries for that reason, because every third-party library you add is extra code which needs to be downloaded and parsed. So the more third-party libraries you load, the more code you have to download. If you use third-party libraries, you also want to consider importing them into your script files and then using Webpack for bundling and code splitting instead of using CDN links. Because if you use CDN links, you can't use code splitting. So bundling code and using lazy loading here really is a great idea for ensuring that your code starts fast and is able to execute as early as possible. Of course, you should also minify code, and Webpack does this automatically to ensure that you ship as little code as possible to your end users. And this is really it. You saw a lot of examples throughout this module. I hopefully could introduce you to how you should think about performance optimizations. You also got some useful external resources where you can dive deeper. And in general, performance optimization is a topic which you can't really master. It's an ongoing journey. There are always new things to explore, and it's also very specific to your exact use case. It's always very specific to that regarding what you want to look into and what you might want to consider optimizing. You can also Google for JavaScript performance optimizations, and you will find many examples, some which you already saw here, some which you didn't. This can also be interesting to learn more about this topic. But always also keep in mind that you shouldn't overdo it. You want to improve your application, you want to fix bugs and leaks, but you don't want to optimize every tiny bit because you could end up with code which is actually longer than before and therefore adds to the bundle size, or you implemented an optimization which isn't optimal anymore in the future. Still, this hopefully got you started, and I showed you some of the most important and critical aspects when it comes to performance optimizations and what you should keep in mind there.